Allora, all'inizio hai detto molto bene, l'immagino diventato verde. Sì, immagino.
Sta registrando. Okay, we are ready.
Okay, so Pavel, are we ready to start?
Yes.
Okay, so welcome everyone. Today we continue with the fourth lecture by Pavel on 3 avatars of mock modularity. Please, Pavel.
Thank you. So let me briefly remind you where we ended up in the last lecture. So we considered a 6D theory labeled by a choice of Lie algebra G, and we considered it on a 6-dimensional space-time of the form M4 for manifold times 2 torus with complex structure tau. And we made a topological twist along M4. And then we considered a partition function of this theory, which also can be equal to the partition function of what is called 4-dimensional Waffer-Witten theory, that is topologically twisted n equals 4 Young-Mills with coupling tau and the gauge group G, big G, such that the Lie algebra of this big G is small g. And we notice that this partition function can be equated to the following quantity in terms of the effective 2-dimensional theory on T2, which obtained by compactifying 6D theory on M4. And so this is a trace over the Hilbert space of this 2-dimensional theory on a circle with periodic boundary conditions on the fermion, or equivalently in the Ramon sector of the theory, -1 to the f, q to the L0, and L0 q bar to the L0 bar. And we would like to use this relation to establish the holomorphic anomaly equation for this partition function by working in terms of this 2-dimensional effective theory. And we want to do this in a kind of simple, less non-trivial example when this group is SU2, the Lie algebra as well. Okay, and but before kind of going into this full-fledged SU2 theory, we want to consider first the case when the Lie algebra is just U1, and then the 6D theory is what is called a free tensor multiplet. Namely, it consists of the following fields, which I will split into 3 groups. There will be scalars, which form, well, let me denote them phi A, and index A goes from 1 to 5, and they form a representation 1,5 of this global symmetry, which we considered in some detail. Spin 6 Euclidean symmetry, and spin 5 R symmetry. And so exactly, so this is scalars in 6 dimensions, but they are all rotated as a vector. They all rotated as a vector with respect to the spin 5 R symmetry. And then there will be fermions in representation 4 plus, 4. And there also will be a self-dual two-form field B. Self-dual means that it's exterior derivative, which is a three-form, satisfies self-duality equation in 6D. So it's equal to the Hodge star acts on it, gives it back. And so since it's a two-form, it transforms under 5/15 representation of spin 6, and it's invariant under spin 5 rotations. It's a singlet under spin 5 R. Okay, but so this two-form field can be understood as kind of two-form analog of the usual one-form gauge field, and it's subject to the following gauge transformation. Similar to the gauge transformation of the more usual one-form gauge field. So we can change this big B by beta such that the d of beta is 0, so it's a closed form, which means that locally we can always represent beta as d alpha, or some alpha, one form, and but this beta it satisfies a certain quantization condition, which is kind of similar to usual Dirac quantization condition for usual gauge field. So the beta, the integral of a beta over any two cycle should be 2 pi times an integer. Okay. And, okay, so this is a description of this free tensor multiplet in 6 dimension, which describes the 6-dimensional series when G is U1. And okay, so now we want to determine what is the effective 2-dimensional series in this particular case. And to do this, first let me introduce the following notation. So B2 plus minus, so this is a rather standard notation, but let me remind you what it is. It's a number of positive / negative eigenvalues of Hodge star operation acting on second cohomology of M4 with real coefficients. So this second cohomology, even if you are not familiar with what is cohomology, this is I will always just understand this vector space. This is a finite dimensional vector space, which can always I will just identify it with a space of harmonic two forms. That's how I will understand this. And then, okay, so this theory, the effective 2-dimensional theory, then has the following fields. And so this the result essentially can be obtained from the exercise before. So let me so essentially what we want to do, so we will be only interested in massless fields in massless fields in 2 dimensions, and they can be, so in general we want to do KK reduction, but for the massless fields in 2D we just need to count the harmonic fields depending on what kind of representations they transform under space-time symmetry. And so in particular, if we start with scalars, which are in representation so here is this representation in the untwisted theory, but so we start with scalars with 1,5, and then we do this representation theory exercise, which we had here, and we see that after the twisting they decompose like this, so they become 2 scalars and a self-dual 2 form on M4. So essentially, these 2 scalars will always give one. They're always one harmonic scalar. and they are B2 plus harmonic self-dual forms. So these fields, so the 6-dimensional scalars then give 2 plus B2 plus real scalars in 2 dimensions. So then, if one can do the same thing for these fermions, using again as a result of the same exercise, but for using the decomposition of this 4 plus, 4 representation, and do the same counting, and this will give us this is absolutely similar, give us 2 plus 2b2 plus right moving fermions. Maybe let me just in case come back to this exercise. So for the fermions, after we did a twist, so they compose in the following representations, and so these two guys, they will give so the scalars on a 4 manifold. There will be 2 of them, so we'll give a 2. Each of them have a harmonic mode. And this will give a 2 right moving fermions into D right moving because they have spin plus 1/2 with respect to 2-dimensional spin symmetry. And these 2 guys give so they transform as self-dual 2 forms on M4. So they will give 2 times B2 plus 2-dimensional fermions, and they are right moving fermions because they have spin 1/2. So in principle, this term can which give us fields which transform as a vectors on a 4 manifold, can also give us some fields, but for simplicity here we will assume that B1 is 0 on a 4 manifold as the first Betti number. So there is no harmonic 1 form or no harmonic vectors equivalently. Okay, and finally we need to deal with this self-dual 2 form, with the KK reduction of this self-dual 2 form, and it will give us the following. So I will write a result, and then I will explain it a little bit. Give us B2 plus or minus, respectively, left, right or left moving chiral compact scalars, which I will denote by xi plus minus with the signs plus minus respectively to the chirality. So how does this can be obtained? So we can always decompose our 2 form as follows. So assuming the B is a harmonic on a 4 manifold, we can decompose it like this. Where HI plus minus is a basis in the space of harmonic 2 forms, such that it diagonalize explicitly the 6-dimensional Hodge star action. Sorry, not 6-dimensional. I'm sorry, 4-dimensional. The harmonic forms on a 4, and the Hodge star acts on the space of harmonic forms on a 4 manifold, and we can choose a basis which diagonalizes the action of this Hodge star, which means exactly the following. In particular, so there will be B2 plus guys which are self-dual, and B2 minus guys which are anti-self-dual. Okay, so this and the coefficient of the decomposition, as usual, will be effective massless 2-dimensional fields, but we have to also take into account the self-duality condition which we had on this B field in 6-dimensional. So it was a condition that this 6-dimensional Hodge star leaves the DB invariant. But if we apply this condition to our decomposition, we will learn, because we know how the 4-dimensional Hodge star acts on H's, and we know that the 6-dimensional Hodge star is essentially a composition of the 4-dimensional Hodge star action and 2-dimensional Hodge star action. So this will just imply that if we plug in the decomposition above, it will just imply the following constraint on our X fields. But if you write it in a 2D, this condition in a 2D complex coordinates, we just choose some complex coordinate 2D, for example, Z, then these conditions above, they just mean that the holomorphic derivative of X plus fields is 0, and the respectively anti-holomorphic derivatives of Xi with minus index is also 0. So respectively, X plus fields, they are right moving, and X minus fields, they are left moving in 2D. But we also have to take into account the gauge equivalence, which we had on a B field. We had a gauge equivalence, okay? And this, so if you want to stay inside the harmonic forms on a 4D, so this beta should have also have the decomposition of this type. Where now the coefficients are just constant because the D should kill beta, both in all 6 dimensions. And we know that the beta, the integral over beta over any 2 cycle should be 2 pi times integer, and this gives us some quantization conditions on these coefficients n plus minus I. And this will imply, so this equivalence on B field will imply the following equivalence on the X fields, where n plus minus they are quantized. Effectively, they mean they can be so the coordinates of some vectors in some lattice. We have a lattice inside the inside this inside the space of harmonic 2 forms, and so this makes X to be compact.
Pavel, there is a question by Erez. Can you explain again how B2 is related to the number of scalars? Okay, thanks. Yeah, so, okay, let's come back to this. Yeah, maybe this was a bit fast. So, okay, we start from some fields in 6 dimensions, scalars in 6 dimensions. And so this is a field transformed in 6 dimensions before putting on any background, before doing any topological twist. So now we start scalars in this representation 1,5, and we do a topological twist. And as we had in this exercise, which was in detail explained during tutorial, how to do this. And but anyway, okay, so here we just look at the result. So here, this part of the exercise. So this 1,5 decomposes as follows into representations of spin 4. This is a symmetry of rotational symmetry along the 4 manifold, and spin 2 rotational symmetry along the 2-dimensional space-time. So these guys, so they are just scalars, and when we count harmonic scalars, they are just for each. They're a single harmonic scalar for each scale. So this just gives two fields in 2D. But this they will transform. This is the representation 3,1 with respect to of spin 4. This is a representation in which the self-dual 2 forms on a 4 manifold transform. And self-dual means that they satisfy self-dual 2 forms means that they satisfy this condition self-dual H star is equal to H. So in principle, the 2 form has 6 components on a 4 manifold, but you can split into 2 kind of irreducible representation of the spin 4 group. which correspond to self-dual component and anti-self-dual. So self-dual, you project self-dual component, you project only on two forms which satisfy this condition. And this gives you three-dimensional irreducible representation of spin form. And now we want, when we do KK reduction, we want to count. So if we want to count massless fields in effective theory on 2D, we just want to account for two forms which satisfy a Laplacian equation, so the harmonic forms. And by definition, the number of these harmonic two forms which are self-dual, it's B2 plus. The number of independent harmonic forms which are self-dual is B2 plus. I hope this answers. Any more questions?
No, I think you can go ahead.
Okay, so this was so we understand how to do when G equals E1, but we're actually, our goal is to deal with SU2 the algebra. And in this case, the 6D theory is in principle non-Lagrangian. So we cannot just start with some Lagrangian and do KK reduction. But what is known about this series on the so-called tensor branch, and I will tell you a little bit what it is. It can be, but roughly it's kind of analog of a Coulomb branch of a four-dimensional gauge theory. It can be effectively described in terms of theory which corresponds to U1 subalgebra of SU2, so U1 Cartan subalgebra with extra interaction terms. So again, we have to use this theory as effective theory, not a kind of UV theory. And so it has some. So this U1 theory which we had before, but before we had a free theory, but now we will have to add some interaction terms in this effective action. And we also want to. There are other caveats that we want to rescale gauge transformations. It's a bit technical, and well, at some level it's important because it's just some rescaling, but it's actually becomes a bit important when we want to get an exact, like precise result. And the rescaling is just what I mean by this is that, so before we have this for the gauge transformations, when we wrote them, we had a extra square root of 2, and this square root of 2 is just have a simple meaning of a length of SU2 root. So in the standard normalization, U1 has root 1, but SU2 has the length of the root is square root of 2. So once we do this embedding, we have to, respective to U1, we have to do this rescaling, rescaling by square root of 2. And so there will be many interaction terms, but the term which will be relevant for us is the following. Well, the bosonic interaction term. And then, of course, it will come with kind of super partners, but which can be recovered from it by supersymmetry. But the relevant bosonic interaction term can be written as follows. So it's an integral. So again, we are talking so far about theory on just on an arbitrary six-dimensional space-time. And it's a form, or it can be written in the following form. it's a B2 form, which we had before, which a certain 4 form, which, okay, to explain what is 4 form, one has to spend a bit of time to introduce some notations. So let me do this. So let me introduce the phi hat A's, which are related as follows to the, this is just the scalars of tensor multiplet that we had before, the 5 scalars. So A goes 1 to 5. And you have this, so you essentially normalize, if you consider this as the scales as a 5-dimensional vector, you just normalize it by to 1 by dividing by the norm. And then we want to define the following covariant differential. So this is just definitions. The covariant differential, it's a covariant with respect to spin 5 R symmetry, meaning that this AABR is a background spin 5 or gauge field. And one can introduce also FR, it's a curvature. 2 form. So A is 1 form and F is 2 form. And okay, now we are prepared to write what this eta 4 is. Okay, it's a rather long formula, but this is the longest, I think it's the longest formula that I will write in my course. So the epsilon symbol with 5 indices. So they are SO5 indices. And then you have the following. So essentially have 3, it contains 3 terms. But essentially what is important is it's a certain explicit expression in terms of the scalar fields of the tensor multiplet and the background R symmetry gauge field. So, and this is essentially all the information we need about this 6D theory, which are associated to SU2 Lie algebra. So it's essentially the same. It can be effectively described. So on the tensor branch as a U1 theory. Okay, so I promised I will tell you briefly what tensor branch means. So we consider the tensor branch as a kind of regime where scalars fluctuate over non-zero values. So this means if we were to consider zero on a non-compact space-time, then you could say the zero it's a kind of it's a phase when you choose a vacuum with non-vanishing expectation values of phis. But you see, so you cannot, this description becomes invalid if all phis, for example, if all phis goes to 0, this blows up and this becomes ill-defined. And this, so this doesn't give you, so something bad happens and it's not known what actually happens when all phis goes to 0. Any questions?
So there's a question by Arlie Shepard. Does the theory for a U1 also exhibit holomorphic anomaly?
No, but some kind of trivial reason that if you consider U1, so yeah, the U1 case is a bit special. For this case, actually, the partition function is just 0. So it just, well, all its derivatives are just, I mean, the partition function is actually just 0. Well, the short answer is that it doesn't. Any other questions?
Yeah, so Ali has a follow-up question. Can I ask why is it 0 actually?
Okay, this is well, this is just because you see that if you just do, I mean, we found what is a two-dimensional theory here, and it just has this. It has always just free fermions, and it's just the one-ish, but because the this index in the Ramon sector is just 0 for whenever you have a free fermion into the, it's just 0. I mean, you can make it non-zero by doing some insertions, and you can get something non-trivial, but it's in this case, in the case of U1, well, you can insert this kind of two fermions, I mean, some fermions to kill these zero modes and make them not trivial, but it's actually, it still will be actually holomorphic. Any other question?
I do not see any questions at the moment.
Okay, so now actually I want to make some digression. I want to kind of give you a crash review of 2D sigma models with 0,1 supersymmetry. Means there is at least one right moving charge, supercharge. And why I need to do this? Because essentially this two-dimensional theory, effective two-dimensional theory for the case of GSE2, it's essentially can be described as an example of such theory. And we can just use some general results about such theories. And we consider actually the kind of the simple case when there is no left moving fermions. So these such sigma models, they can be described by the following data. X, it's a manifold equipped with metric G and a closed 3-form H. So it's a 3-form in this on the X. So this X is usually called a target space. So this is the sigma models. Supersymmetric sigma models. They briefly already appeared in the Tisch course, but I will review it anyway to remind you. And then, okay, so we have this data, and then the fields of the theory are the following. So there will be scalars, which can be understood as a map from sigma 2 two-dimensional space-time to this X, the target space. So sigma is 2D space-time. And there will be also right-moving, the superpartners, which are right-moving fermions, which is known by psi. So informally, one can say this is the fermions valued in the tangent space of X. But if you want to be precise, these sections of the following bundle, so you have to, by the map phi, you pull back the tangent bundle of X on sigma 2 on two-dimensional space-time, and you tensor it with S2 plus sigma 2, which is a bundle of right-moving fermions, right-moving spinors on sigma 2. So roughly, you can see this kind of have in mind the following picture. So you have a kind of a two-dimensional space-time, or sometimes called source or worldsheet, and it's mapped to X, a fixed target space, and so you can kind of draw its image somewhere here, and then if you can consider some point on the space-time, you have an image of this point in the target, and then you consider tangent space to this point in X, and this is where your fermions at this point in the source are valued. So the fermions here are valued in the tangent space to this to the image of this point in X. Okay, but of course we can decide to choose coordinates, and in coordinates one can explicitly, for example, write everything in particular action. Has the following form. So I'll assume that sigma 2 so far here is flat, but of course you can promote it to a curved space. Okay, so first there will be the following part. So G here is a metric, and B, what is B here? B is the following two form. It's a two form on a target space on X. So since dH equals 0, we can locally always find two form B such that H is equal to dB locally on the target space. And this is our so this term is often referred to as Weizsäcker term. And then there will be the following term, kind of kinetic term. So that was a kinetic term for bosons, for scalars, and there will be the following kinetic term for fermions, and then there will be the following interaction term. Well, I mean, the previous terms, they also contain interaction terms if you expand G and B in the scalar field. So H here, Hij, is a component of our 3 form on the target. And well, gamma here are just Christoffel symbols for Levi-Civita connection for this metric G, which we chose. And then the supersymmetry acts as follows on the fields. So it's very simple. So Q on phi I gives me psi I, and Q on psi I gives me minus anti-holomorphic derivative of phi I. And it's a nice, straightforward exercise to show that this action is invariant. Is invariant under these transformations. Okay, and then we also can consider kind of right moving component of energy momentum tensor, meaning this is a component of energy momentum tensor with respect to z bar, and it's customary to denote it by just t bar, and okay, it has the following explicit expression. Oh, sorry. J R d bar J plus half. Again, this is something you just you can obtain using the general usual methods starting from the action. And there will be also a supercurrent. So essentially, this is a Noether current for Q, for the symmetry Q. So again, you can obtain it by using again, standard methods. So supercurrent G bar, and it has the following explicit expression. And so this is actually expression for supercurrent, which we will need later. But they are closely, the right moment, energy moment tensor, supercurrent, they're closely related. If I act by Q defined above on G bar, one can show that the result is up to simple coefficient is just T bar. So again, this is an easy, straightforward exercise to check this. Okay. Any questions?
I do not see any questions in the chat window, but maybe people want to ask.
Okay, I can then go on, I guess. Okay, so, and then if X, if the target plane is closed, meaning it's compact and it has no boundary, then if you consider, so the index of such theory, so the theory which is sigma model with some given target are denoted by sigma of X. So the index of the theory, which again defined as we had before, it's trace or -1 to the F, Q L0, Q bar to the L0 bar, where H is the Hilbert space of the theory on a circle with periodic boundary conditions on fermions. So if X is closed, then this is index is holomorphic in tau. Again, one can argue this, for example, just because of the fact that the spectrum is discrete, the spectrum of L0 and L0 bar is discrete, and because of the cancellation of Boson's fermions, the dependence on Q bar drops out. And moreover, it's actually, yeah, just like we're not going to need this before, but since we are here, let me just mention that, I mean, in this case, one can actually write an explicit formula for this index in terms of just geometric data that we had. It's actually just a certain topological invariant of the target, which is called in mathematical literature, which is called elliptic genius. And one can explicitly write it in the following compact form. It's a certain integral of a certain form on X over the target space, where R is essentially a Riemann curvature tensor, but it's understood in the following way: it's a curvature to form on X valued in SO into orthogonal algebra corresponding to the dimension of X, and then and the theta function. And the theta function is just defined by the following formula.
So Pavel, Ali is asking, can the action of the 2D 0,1 sigma model be derived from the only term in 6D that you wrote down?
Yes, yes. I will elaborate on it later, but yes, the answer is. Well, I mean, okay, well, let me say yes. Okay, yes, the answer is yes. Well, there might be some kind of correction terms which will bring it out of the sigma model of this type, like some sort of high derivative correction, but we're not going to need this. But the action, yeah, the action of the form, the terms of the form which I wrote, they all can be obtained just using that. Okay, and so anyway, so but if X is non-compact, this is not true. And however, one can explicitly write what should be the derivative with respect to tau bar in this case. Well, in the case here, I assume that x asymptotically looks like R times some y space, meaning x, yeah, there's a picture kind of similar to what I draw. So x looks as some sort of neck at the infinity of the form R times y, where y now is some complex space. And then one can write the following formula. So in particular, it's recently appeared in the paper by Garrett and Johnson-Fate. Although they consider it kind of a more general setup than just sigma models. So this, up to some simple factor, this anti-homomorphic derivative can be related to expectation value of G bar in the sigma model in Y. So namely, this is a 1-point function on a 2 torus in a sigma model with target Y. Okay. Okay, let me very briefly, since yeah, I have to finish soon, let me very briefly kind of, so you can find more detailed explanation how to obtain this formula in the lecture notes or in the paper, either in the paper by Kaphalkar, Witten, and myself, or in the Gayotto Johnson-Fate paper. But let me briefly give you the idea. So first, if we take this derivative with respect to tau bar, this gives us just by, if we start 1-pass integral, it's just derivative of tau bar just acts on the action. And but the derivative of the respect to tau bar, it can be related to the derivative with respect to anti-holomorphic component of the metric. So this is a metric on sigma 2. And then by definition of the energy momentum tensor, so here I'm suppressing some non-important numerical coefficients. It's a 1-point function of the energy momentum tensor. So far we are still working in the sigma model with target x in the original sigma model. And then we know that T bar is Q of G bar. G bar is a 1-point supercurrent. Sorry, it's a supercurrent. And probably the next step is the most non-trivial. Then this thing can be expressed as a 1-point function of a supercurrent in a sigma model with target y times a certain contribution of a certain simple factor, which I mentioned at the moment. But let me first say how can we go from x sigma model with target x to sigma model with target y. So suppose we consider restriction to 0 modes. Phi 0 modes in our sigma model. Let's denote the 0 modes phi 0i and psi 0i. So it's just a constant fields on sigma 2. Well, here sigma 2 we actually take to be 2 torus. Then this q, which we had above, it's easy to see that it acts as follows. Just q acts on phi 0 gives us psi 0, and q acts on psi 0i gives us 0. The right hand side was of the full psi, it gives you derivative of phi 0 by, but it is strict on a constant modes, just gives you 0. So this means that this q can be interpreted as a differential, as an exterior derivative on x acting on the forms on x, if we assume that so phi 0 can be interpreted as coordinates on target x, and this psi 0i can be interpreted as a differentials with respect to these coordinates. And then q is just a d acting on x if, well, if you assume that And also we can know that if you have an integral over zero modes of some function of those zero modes, then this integral can be interpreted as just integral over x of a certain form corresponding to this function, right? Under this correspondence, if you just replace if you replace all psi i's by these d's, then this integral over d's can be understood over all both bosonic and Fermionic zero modes can be just understood as integral over the corresponding form. And then this means if you have something, so we have q here, we have q of something, and if we restrict on the zero modes, we will have a integral over x of d of something, and then this can be using the Stokes theorem. This can be reduced to integral over y of this something, and that's why essentially we get this piece. So we get rid of q using the Stokes theorem, but now we can see the sigma model with target y. So this will happen if we just think about zero mode. But of course, there will be also contribution of non-zero modes. And the extra, which gives you extra factor, and this can be this will have two parts. So they have a bar eta bar of tau times 1 over tau absolute value of eta squared. And so this is these extra factors can be put as a mismatch between non-zero modes in target x in sigma model with target x and non-zero modes with target y. Because the mismatch here, they differ only by x and y, they differ only by a single direction. There's a single extra direction, and this single extra direction, when we get a contribution from non-zero modes corresponding to this direction, we just consider the contribution of non-zero modes of a one scalar, non-compact scalar, and this is well known to be this. This is a partition function of a single scalar. If you remove this, if you remove the integral over zero mode, which is kind of gives you volume, and this gives a partition function of its corresponding superpartner, right moving fermion, also with zero mode removed. And if you combine this, if you multiply this together, this will give us this just 1 over eta holomorphic. Okay. But of course, this is a very, I'm suppressing very many details here, as I mentioned. And now we are essentially ready to do everything. And so we can come back to this theory, two-dimensional theory, where we take a four manifold to be CP2 and the Lie algebra to be SU2, and we consider this two-dimensional theory obtained by starting six-dimensional theory on tensor branch. And so we just use, so first to determine what the field content, we just use this result which we had on a general manifold, this result for a single free tensor multiply. Okay, to do this, we need to first let me remind you, there is the space of for CP2, the space of Seldul harmonic form has single generator. To form omega. So in particular, you can, if you take a standard Fubinish 2D metric on CP2, this omega is a standard Keller form. And so it satisfies its self-dual, and it's normalized as follows. So integral over CP2 is equal to 1, and integral over, so all two cycles can be generated by just CP1. So the integral of omega is 1. So we will need this to know how this gauge transformation are quantized. So in particular, this means that B2 plus equals 1 and B2 minus is equal 0. And there will be three scalars, phi I, I goes from 1 to 3, and there will be 4 fermions. So I'm just using the previous result by plugging in these beta numbers, 4 fermions, and there will be one right-moving scalar, x plus, or I can also denote it by 4 to kind of combine all scalars together, which satisfies the following periodicity condition, which one can easily deduce from this property. And so the theory, you can see it's almost sigma model with target x, where x is R3 times S1. So R3 is just these 3 scalars, and S1 is this periodic scalar. So n here is integer. Almost means that the only caveat here is that this scalar, which is valid in a circle, it's right moving. But this is okay because we're only interested in the action of right moving superstring. So left, we can throw actually way left moving part that doesn't affect the the supersymmetry action. And this x in particular, it can be asymptotically, it can be said that it looks like R times S2 times S1, where R is kind of radial direction. R is a radial direction of R3. So R3 asymptotically looks like R times S2. And this is why.
So Eric is asking, what happens with B1 here?
Well, okay, yeah, thank you. So B1, if B1 for CP2 is 0, it's simply connected. There is no B1. Okay, so yeah. So now we have to deal with this interaction term. In 6th dimension, we had what I wrote. It was this term. So it's the integral over CP2 times sigma 2. And then one can just, if one reduce all, do this KK reduction of all 6D fields to 2D fields, and just explicitly integrate over CP2, one can show that we will obtain the following 2D term of the following form. So this is this Bezzamino type term, which depends on this on the certain 2 form B on a target. So the H, if we introduce this H, which is dB as before, then H can be written simply. One can show that H is the following. It's up to simple factor. It's a 3 form, which is a product of a volume form on S2 times the volume form on S1, which are normalized to 1, meaning that if you integrate over S2, we get 1, and if we integrate over S1, we also get 1. And then we can just plug in this data which we had in the formula which we had before for the anti-homomorphic derivative. Again, I will suppress some simple factors. But what we want to calculate now. We want to calculate the one point function of a supercurrent in the sigma model with target y, and so as we had the explicit expression for this, and it will in particular contain the following term, and there will be some the other term which will actually are not going to contribute. One can argue that. Okay, so now we want to calculate this 1 point function, and this is actually easy to do. So again, one can split your kind of contribution integral. So this is given by some path integral of the sigma model, but can again split the contribution from 0 modes and non-zero modes. And the contribution from 0 modes you will end up just calculating the integral over h over y over the target y. So this is using the same identification that we had before. If you identify 0 modes of psi with differential of coordinates on the target. So this is a contribution from 0 modes. And then there will be also a simple contribution from non-zero modes. yeah, I'll just, yeah, I'll finish this formula and I will stop. So, okay, let me write it and then I will briefly explain what these factors are. And so this factor is maybe I should write it. So this factor corresponds to 3 fermions. So this counts contribution of non-zero modes. 3 fermions which live in the tangent space of this target. So this corresponds to scalars, 2 scalars which are valued in S2, and this is correspond to scalar valued in a circle. So because it's a scalar valued in a circle, you will get this kind of sum over momenta, roughly speaking. Well, this is n is actually some, well, it's a linear combination of momenta and YD number. And okay, once what is left is just to calculate this finite dimensional integral using the explicit expression for h, and you end up getting the result, indeed the result which was predicted from mock modularity. Okay, so I stop here.
Okay, let's thank Pavel. Okay, are there any questions? Sorry, I have a question, Pavel. So this is very basic and probably you already explained it, but maybe you can briefly explain again. What happens with a region where the phi's are close to 0?
Well, from the point of view of 6D theory, you get kind of your depletion breaks down. Well, essentially, you can imagine the guess I'm going to get some new gapless decrease of freedom, and this is a point. If you exactly go to phi 0, this is a point where conformal symmetry gets restored, and you get some highly interacting conformal symmetry. And so this kind of this bad point in 6D translates into kind of bad point into origin of the sigma model, where you also see this kind of simple kind of description in terms of sigma model. This should break down, so you get some at this point you get some additional degrees of freedom, which you don't know actually explicitly how to describe. But this doesn't matter, since we by this kind of argument, we show that these holomorphic phenomena can only come from the boundary at infinity. And for near the boundary at infinity, we know we can use this still valid. We don't care what is the bad point with additional degrees of freedom, which every time. So globally, you actually cannot use, you wouldn't be able to calculate the full partition function using the sigma model description. It wouldn't be false.
I see. Okay, thank you. So there is a question by Eric. Is there an alternative to the tensor branch?
Well, in this 6D 2,0 theory, no. I mean, there is either a tensor branch or this conformal point. Essentially, it's just tensor branch, and at the origin there is a conformal.
And
well,
then, yeah. And then another question by Eres, can this anomaly cancel by a counter term at the price of something else?
Can this? Well, in principle, maybe yes, but I'm not sure if you want to do this because again, from physical point of view, you want. I mean, this is not really something bad. So you want to. Well, you maybe you can introduce some sort of counter term which makes the series holomorphic, but it should then breaks down the S duality. But we don't know to break S duality. We know that the physical theory, the good physical theory must have S duality. So we want to. We don't want, from physical point of view, we don't actually want to trade holomorphicity to S duality. S duality is more. It's more.
Okay, I do not see any other questions. So maybe at this point, we should thank again Pavel for the very nice set of lectures, and also Atis, and together they gave this very nice course. So thanks.
Thank you.
And we will resume in about 10 minutes from now with Ahmed's fourth lecture.
Erasing the hello seemed very serious.
Hi, Ahmed.
Oh, sorry, I was muted. Sorry. How are you?
Fine, fine. How are you?
Doing well, thanks. Should I share my screen?
Yes, sure, please.
Hi, Kyriakos.
Hi, Eddie.
How are you?
Fine, fine. And you?
We cannot see you. Eddie.
Yeah, okay. Now?
No, we cannot see you.
No, it did not. Okay.
Nice. Yeah, we saw you briefly.
Okay.
Can we start, Ahmed?
Yeah.
Okay, so we're very happy to have Ahmed, who will give his fourth lecture on quantum black holes. Please.
Thanks, Kyriakos. So in this last lecture, hopefully we'll finish the story. Let me begin with a brief recap. So in the last lecture, I introduced this gravitational fine-grained entropy formula, which is, I guess, sometimes called the island formula, which has some pretty remarkable features. So the main one is that it generates the page curve and produces results that are consistent with unitarity. This talk is going to be about two things. The first is going to be brief. It's going to be about how this formula realizes the Hayden-Preskel protocol. I discussed this very briefly yesterday in response to a question, or sorry, 2 days ago. And the second part is going to be about how this formula is derived from non-perturbative contributions to the path integral, the full gravity matter path integral. Okay. So let's begin with the Hayden-Preskel protocol. So what Hayden-Preskel argued was that if you think of a black hole as a quantum system of strongly interacting, roughly S. Bekenstein-Hawking number of degrees of freedom, then you expect that after the page time, once the black hole is sort of maximally entangled with the radiation, that if you throw a small message into the black hole, it should be transferred to the radiation after a scrambling time, which is defined as beta log S. So the goal is to try to see how the island formula reproduces something like this. Before I get into that, let me briefly comment on a notion first introduced in holography something called subregion duality. Douglas is going to talk more about this, I believe, in his lecture today. The main claim is the following: that if you have an entropy formula, as I've written here, S of some region Q in the bath is equal to some area term of some surface plus a von Neumann entropy involving a region in the bulk, then there's a sense in which this region in the bulk, sigma x, is can be thought of as dual to the bath region Q. And the way to see that is basically that this formula tells you that the state of Q, or rather some properties of the state of Q, are sensitive to the state of sigma x. In particular, if you place suppose a maximally mixed qubit in the ADS region in sigma x, then that will raise the entropy of Q by log 2. Right? So you can just apply this formula. So this is sort of so far this is just a very rough argument to say that you can reconstruct X from Q, but Douglas will give you a much more precise derivation of this fact. So let's apply this to our situations. I'm going to consider two examples. So in example A, here I have on the right-hand side, I have my eternal black hole. I'm imagining here that I'm computing the entropy of some region Q in the bath that contains the ADS boundary. Using the rules that we discussed before, you'll find that the quantum extremal surface extends into the bulk, or rather the quantum extremal surface extends into the bulk and at some location X. And the statement of subregion duality is that everything inside this diamond, which is often called the entanglement wedge of Q, is dual to Q. Okay, this entanglement wedge is simply defined as the causal development of the union of sigma x and Q. All right, so that's what we learn about subregion duality. Now you can ask about how information which starts in Q can somehow leave Q. Suppose we do the following experiment. So the first let's focus on the intervals. So I have some interval at t equals 0. That's Q and its associated X. But then you can consider Q and its associated X at some much earlier time. Okay? Its X is going to be located somewhere there. Now, suppose that you have some message, some pulse of energy or a qubit or whatever it is, that begins life somewhere inside Q and then falls into the bulk. From this picture, it's clear that that at this time it's part of the system Q, but at the origin at time t equals 0, this pulse is outside of the entanglement wedge of Q, and therefore Q loses access to this message. And you can show that the minimum amount of time after which any message gets lost is precisely the scrambling time. And this is something that I've put as an exercise for you to solve in the tutorial. So you'll get something that looks like this. Delta T is beta times log of SBH, the Begistein-Hawking entropy, minus S naught. This is just a special feature of near extremal black holes, that it's only the thermal part of the entropy that contributes to this process, to the scrambling. The other case, we can think of now the situation of computing the entropy of the union of the two boundaries of the black hole and also of the radiation. So let's focus first of the computation of the entropy of the two boundaries. Then we know that there's a transition that happens in the quantum extremal surface. At t equals 0, it was the trivial saddle that contributed, but at some later time, after the page time, the disconnected surface is what dominated the entropy. And now you can see how information that was part of the black hole, part of the boundary degrees of freedom. So this pulse here, this information, this particle is part of the entanglement wedge of the two boundaries. But after the page time, it's no longer part of the entanglement wedge. It gets, the black hole loses access to the information about this message. And similarly, after the page time, if you throw a message, this is essentially what we did in the previous slide, but if you throw a message, you will lose it after a scrambling time, and so on and so forth. So where does the information go? Well, for that, you need to look at the computation of the entropy of the radiation, so the complement of the black hole. And then at t equals 0, there is no island, so the information is part of the black hole. But then after the page time, you have an island. And the message is now part of the island of the radiation. And so therefore, you can think of it as becoming part of the radiation. So these two pictures combined tells you how information thrown into a black hole ends up in the radiation. It ends up in the radiation because the radiation claims the interior after some time. Any questions about Hayden-Prescoe? Okay, if there are no questions, let me discuss the second topic, this lecture, which is about deriving the generalized fine grained entropy formula or the island formula. So the key is that we need to allow for dynamical gravity when applying the replica trick. Let me just give a very brief example. Suppose we compute trace rho, just trace rho. We know that that's just equal to 1, but it's instructive to think about this. So trace rho is just given by the full path integral. So you integrate over the metric, the dilaton, and psi here are the CFT matter fields. So far, the limit in which we have been working is the so-called semi-classical limit, or where you sort of focus on what's often called the Hawking saddle of this path integral, where you only look at the saddle point where the metric saddle is given by the Euclidean black hole, the hyperbolic disk, or just G80S2. Okay, and then the remaining path integral is simply the matter path integral on this fixed non-fluctuating geometry. Okay, this is what we've been working with in the first 2 lectures. And the picture you draw is something like this. So here's the path integral. Before I've drawn the path integral, the boundary of the flat space path integral as a circle, but now I'm drawing it as a rectangle just for convenience. So this path integral describes one where you have flat space out here and just an ADS2 in the center. And then if you continue this to Lorentzian space, you get the eternal black hole that we've been working with. But in the full path integral, you should allow for all possible gravitational configurations that are consistent with the boundary conditions in this circle. So you shouldn't just focus on one single saddle, the Hawking saddle or the semi-classical saddle, but the path integral includes all possible configurations of the gravity region, subject to the boundary conditions. Okay, so that's the philosophy here. Now let's discuss the computation of the Renyi entropy. We're going to do this with an example. So let's consider the case where we compute the single interval case, the single interval that contains the ADS boundary. So we want to compute the replica trick, the Renyi entropy using the replica trick. Sorry, the entropy using the replica trick, meaning just the Renyi entropies, which is equal to this ratio of path integrals. And if you recall from the first lecture, the first step of this process is to consider n copies of your theory identified across the interval that we are trying to compute the entropy of. So far, if you notice, the gravity region here is not shaded, so it's not filled in. So far, there are just boundary conditions. The first step to evaluating this is to go to what is called the covering space, where you remove the branch cut. Because of the identification at because the branch cut hits the boundary, in the covering space, the length of this circle is no longer beta, but it's beta times n, where n is the number of replicas. Now we're ready to consider gravitational configurations in this region. It turns out that for this case, the only relevant one is the disk. It just is the hyperbolic disk in the covering space. So we have now ADS2. We have filled in the gravity region. Now you can imagine going back to the original coordinate system, you can undo the cover. And when you undo the cover, what you find is that the branch cut, which ended on the ADS boundary, now extends into the ADS2 region. So before it was from 0 to B, now it becomes from minus A to B. Okay. Okay. I should say here that for this talk, and also in what I just discussed, I've been assuming a replica symmetry. So the gravitational configurations in this gravity region all obey replica symmetry. Let me make a comment here that you can ask, where is this minus A in this picture? This minus A is really the origin. So A and B are the fixed points of this Zn symmetry. In this picture, one fixed point is the origin, and the other fixed point is at infinity. So there are sort of wedges here. Each wedge corresponds to a single copy of the theory. Also more terminology. So this thing I'm going to label as the branched cover, as opposed to the replica manifold. The replica manifold I'm going to label by Mn tilde, and the branched cover as Mn, as Mn, which is equal to Mn tilde mod Zn. Any questions about the setup?
I'm sorry, what is the interval that you actually wanted to start with in the actual picture of the...
Good, so that was supposed to be indicated here. So the interval is one that starts at the ADS boundary and ends at some location B in the bath. It's, I'm gonna go back a few slides. Sorry, go on. Yeah,
no, so I'm a bit confused as to how it gets extended into the bulk, that part, you know, after the replica tree, after the branch cover.
Well, I'm undoing the, now I'm just undoing the cover. So if you look at, so let me see, how should I say it? So is it clear to you how we go from this picture to this picture and back?
Yes, I mean, this is the standard Cardi-Calabrese way of calculating Renyi entropy, right?
Yeah, well, here, there's some coordinate transformation that removes the branch cut and takes you to a space where there is no branch cut.
That's correct, yeah.
And now obviously if you can go back and reintroduce the branch cut. Now my claim is that if you first fill in the ADS region and then try to undo the branch cut, then try to put back the branch cut in the bath region,
right,
you'll be forced to also introduce a branch cut in the gravity region.
I see.
That's the claim.
Okay. So Ahmed, there's one more question about these points. So Hamid is asking, does B represent the location of Q?
Yeah, so Q in this case is an interval that goes from 0 to B.
And there's one more question from Christian. Do you have something to say about spontaneous breaking of replica symmetry?
I do not. Douglas will discuss this in detail.
And I see a raised hand by Arif. Please go ahead.
I'm sorry, but it's still not clear how the branch point moved from the boundary of ADS to the bulk. So what happened to the, if you're doing just, let's say, instead of n, just 2 copies, can we see exactly how that happens?
Well, let me see. Maybe, so let me go to this.
Suppose you just do 2 copies, does it move a little, or it's just even in 2 copies you just get at in the bulk?
Even for the 2 copies, it moves in. I mean, the idea is that, so here, here in the branched cover, if you, well, let me see. Each sheet of the branched cover corresponds to a wedge in this picture. And, well, let me see. If you start in this picture in the covering space with the filled-in space, each copy of the theory corresponds to a wedge. And so therefore, if you only focus on a single wedge, you'll have to have a branch cut. Maybe that's the way to say it.
Well, I mean, a branch cut was there, but the thing is, when you undo the cover, how does the branch point move in the bulk? I mean, it was at the bound. One of the points was at the boundary of ADS, right? So, so suppose you were not filling. Is it is it because you're filling the bulk with some geometry, or?
Yeah, it's because I filled in the bulk with the geometry.
But what non-trivial thing happens? Is it? Are you telling me this is just a matter of calculation? You do it and you see it, but.
I mean that's obviously true, but should be a
yeah.
simple way to see it.
Yeah.
Let me see. I'd say let me move on, and if an answer comes into my mind at some point, I'll address this point again.
Sure. Okay. Thanks.
Okay.
One more question by Upamanu. Please go ahead.
Yeah, so this is regarding the previous questions about how the point moves inwards in the ADS to boundary, from the ADS to boundary to inside. So I was wondering, Ahmed, whether it would be useful to think about it this way, that the first picture and the second picture, they're essentially the same. But in the second picture, what we are actually doing is appealing to the holographic nature of the boundary. In the first picture, when we extend it to the boundary of ADS2, we're actually computing the sort of entropy of the whole region. But when we want to describe it holographically, the boundary, whatever degree of freedom is on the boundary, that gets automatically translated into some condition within the bulk. Do you think that would be a way of looking at it?
That is a way of looking at it, correct.
Thanks.
But let me move on for now. Okay, so in this slide, the only thing that changed is that I filled in this region. So I've extended the branch cut into the gravity region up to some point there. Let me make a set of comments on these branch points. So the left slide here was the right slide of the previous page, or sorry, the left page is the right page of the previous slide. Anyways, so just a few comments. If you look at point B, the angle around point B on the replicated manifold is 2 pi n. So the metric there has it truly has a conical singularity. If you look at this from the branched cover perspective, on a single sheet of the branched cover, the metric is smooth in the sense that the angle is 2 pi. That's what I meant. If you look at the point A, however, on the replicated manifold, point A is actually not singular. The angle around point A is actually 2 pi. However, in the branched cover, the angle around A on a single sheet is 2 pi over n. So the metric has a conical singularity there. One more comment on A is that the different locations or different values of A, so different locations of where this point is, correspond to different gravity configurations. When you look at the path integral on G and phi, for example, in the replicated manifold, in terms of the branched cover, they can be sort of rewritten as some integral over A and integral over other quantities. But really, the value of A should be thought of as a gravity, as a labeling a gravity configuration. Okay. See. And now, as I was just saying here, the location of then what we'll find, or rather the limit or the regime in which we're going to be working, is that we're going to consider saddle points of A in the path integral. Well, in fact, saddle points of the path integral in general. And the location of A is going to be fixed by those saddle points. So the path integral is something like this: e to the minus I is a function of A and also of other fields. We will approximate it as some sum over saddles. And obviously there are non-saddle contributions, which we're going to ignore. And we will find that the location of A will ultimately be fixed by the equations of motion. Okay. Any questions up to this point? Okay, so I will move on.
Sorry, Arif. Yeah,
Yes.
Arif, go ahead.
So when you say A is fixed by equation of motion, so are you going to fill up the bulk geometries with some singular configurations? And because, so these saddles, would they, some singular configurations would be allowed in the bulk in order to have the branch point there?
Sorry, did you say singular configurations?
Yes.
So it's the configurations I'm going to consider are not singular in the replicated manifold sense. The replicated manifold, the angle around A is just 2 pi. The metric is smooth everywhere. However, if you look at the theory on the branched cover, yes, there is a singularity, but that's not a real singularity. It's just because you're working in a weird coordinate system. But I will have more to say about that.
So let's see, in the branch cover, you said at point A, you have a conical singularity, 2 pi by n.
Mm-hmm.
So if it's conical singularity, then it's a conical singularity. It's not a coordinate thing.
No, but you should, well, there are, how about this? Let's look at the theory on the replicated manifold. So we are in agreement that there's no singularity on A. Is that correct?
Well, okay, I would trust you with that. I mean, I don't know how that A comes about so far, so I don't really know. But yeah, well, in replicated manifold at the origin or inside ADS bulk, there's no singularity. Yes, that much I can.
Perfect. There's a coordinate transformation you can do, which puts a singularity on A. But however, it also introduces extra terms in your action, which insert something called a cosmic brain, a source for that singularity.
Okay, so fine, yeah, I see. So just trying to guess what might come ahead. So you're going to fill up the bulk allowing, I mean, having those configurations in place. So, okay, the brain will be in place in the bulk.
Mhm.
Okay.
I have more on that on the
Yeah,
next slide.
yeah, sure. I'll wait. Thanks.
Sorry, one more question by Hamid.
Sorry, as I understand, you're considering the entropy associated to a region in the flat region, right?
Correct.
So, but in the end, you have a contribution also in the ADS region that will come about later, or have you considered?
Good, good. Well, we're trying to derive how the entropy in the flat region gets a contribution from the gravity region, and we've already seen a hint up to this point that the branch cut gets extended into the bulk, and you will see from my next two slides how the full formula comes about.
Okay, thanks.
Okay. If there are no further questions, I will move on. Okay. So, so we considered the configurations that computed trace row to the n. Now let's use that to compute the entropy. So the entropy, you can convince yourself, well, it's partial n times on trace row to the n, which you can convince yourself from the definition of trace row to the n that it's equivalent to the derivative of log zn over n. On any, now let's consider log zn over n. On any saddle or gravitational saddle, log zn over n is going to be something like minus 1 over n times the action of jt on the replicated manifold, plus the log of the matter partition function also on that replicated manifold. Okay, so far I'm stating everything in terms of the replicated manifold. Now let's express everything in terms of the orbifold theory. And the JT action on the orbifold theory is so 1 over n times the JT action is going to be just well, one term is just a JT action on a single sheet of the branched cover. The reason is so that it's a sum of n JT actions, one on each sheet, but that n cancels with this n. Remember, and they're all the same because I'm assuming replica symmetry. But the theory on the branched cover on a single sheet has a singularity at A. So this is the thing that was mentioned a few moments ago. And therefore, from the perspective of the theory on the branched cover, you need to include some sources for this conical singularity. These are the so-called cosmic brane terms. Okay? So that's going to be given by basically just the dilaton divided by 4g Newton at the location A or minus A or whatever. And you can sort of just for sanity's sake, so it's clear that if you take n goes to 1, the cosmic brane terms should disappear because the singularity should disappear. And indeed, that's what happens. This thing goes to 0, and then the replicated manifold just coincides with the branched cover. Okay, so this is the theory that you should work with if you want to work in the orbifold theory. As for the matter path integral, it can be expressed on the branched cover in terms of a correlation function of twist fields, as we've discussed before. Okay, so yeah. So it's just in this case it's a correlation. It's a 2-point function of the twist fields in the orbifold theory. Are there questions about what I just said?
Could you just want to make sure that I got it. So are you saying that the first term on the right-hand side of this equation that you're pointing at, the first term is singular and the singular contribution is canceled by the cosmic brain term? Or you're saying the, okay, so in all, so there is no singularity in 1 over n times ijt on m and tilde is so okay. Okay, thanks.
Yeah.
Ahmed, there is a question in the chat window from Berhad. Are you ignoring the back reaction of the cosmic brain?
No. The fact that the angle here is 2 pi over n is precisely because the cosmic brain has back reacted. Okay.
I'm sorry. So that then it means what I was saying was not correct, because I thought the angle was 2 pi by n, but then the back reaction of the cosmic brain is canceling that. So that's not what's happening.
No. It's canceling the contribution of that to the action. It's not saying that there is no singularity in the space-time. So naively, if there's a singularity in the space-time, then ijt is infinity, or is equal to something. No, sorry, I misspoke. I didn't mean infinity. I just meant that there's a hint of the singularity in ijt, but that hint of the singularity gets canceled by this term. That's what I meant.
Okay. All right.
Okay. I'm running kind of short on time, so maybe you should hold off the questions for a few minutes.
Okay.
Yeah, sure.
Okay. So this is going to be a bit technical at this point, just for this slide, which is to evaluate the entropy from what I just said here. So the left page here is the right page of the previous slide. So let's evaluate this. So let's first look at the case for n equals 1. N is exactly equal to 1. We know that the solution on the disk is simply the Euclidean black hole, or just the ADS2 or the semi-classical saddle. In this case, the JT action on the replicated manifold just becomes the JT on a single sheet. JT action on a single sheet, there is no cosmic brain, etc. The CFT term, the correlation function of the twist field just becomes a correlation function of the identity. Because we've taken n goes to 1, the branch points are no longer there, so there's no dependence on A or B. Okay, so it's good. But now let's deform away from this configuration. So n is approximately equal to 1. It's 1 plus epsilon. You can think of the configuration now as a small deformation from n equals 1. Okay, where we're doing an analytic continuation of n. And let's look at this term by term. The JT action 1 over n ijt on m tilde is going to be equal to the n equals 1 solution, or n equals 1 value, plus the deformations. The first deformation, when you deform n away from 1, you're making a small deformation of the metric. So you'll get a term which is proportional to delta g of n, delta gn. But this is a first order variation with respect to the metric. That's going to be proportional to the equations of motion. We're ultimately going to set the equations of motion to be 0. So we're working on a saddle. And so this term is actually just going to cancel. And then now the cosmic brain term is no longer 0 because we're near n equals 1. It's going to look something like this: 1 minus n times the dilaton term over 4g Newton. So that's the gravity part. Then comes the matter part. Well, so if n is not equal to 1, the twist fields are back, and this correlation function is going to be one that is evaluated on the n equals 1 semi-classical saddle. So now we have a 2-point function of twist fields on the semi-classical saddle, that's nothing but the von Neumann entropy, or rather, well, because we're working near n equals 1, we've sort of automatically taken the derivative. That's why it becomes the von Neumann entropy of the interval between minus a to b multiplied by 1 minus n. Okay, so again, if you look at these equations and take n goes to 1, these terms cancel and you get back this. But now we're working n near 1. Therefore, you can take these quantities and plug them back in to trace rho to the n, the Renyi entropy. And what you'll find is something like this. It's going to be the sum over I, one for each saddle, of e to the minus n minus 1 multiplied by the generalized entropy with respect to minus a and b. Okay. So in principle, there could be many a's, but it turns out that in this particular situation, there's only one saddle, but here I'm writing it more generally. And now we can understand the full formula that we saw before. So we saw how the generalized entropy just comes about. And we understand the extremality condition as a saddle point condition on the path integral. Remember, A can be thought of as a gravity configuration, or rather it's a parameter of the gravity configuration, and therefore it must be a saddle point with respect to varying that parameter. And that's why partial AI on Sgen has to be equal to 0. And we can also understand the minimality condition. It comes from the fact that these different saddles, before taking n goes to 1, are competing. Right? So they're each weighted by the generalized entropy. And the one with the smallest generalized entropy is the one that's going to dominate this sum. And that's why the minimality condition arises. Okay, so that's the derivation. I was going to give a few more examples after I take questions on what I just said.
There is a question by Erez. If you were to integrate not from b to 0, but something smaller than 0, what is the justification to consider connected bulk configurations?
Small 0 or greater than 0?
The question is about smaller, but maybe Erez can unmute and ask the question and clarify.
So the question is, if you don't integrate from B all the way to the boundary of the flat region, but something smaller than that.
By smaller than that, you mean into the ADS region?
No. Not up to the boundary, but before the boundary, still
Good.
in the flat space.
That's going to be my next example. So let me hold off on that.
Okay, Pedro, go ahead.
Okay, can you hear me? Yes.
Yes.
Okay, maybe you can disregard this question because it's related to bibliography, but in the original paper by Dong, I think in 2016, when he introduced this cosmic brain term, in the end, I ended up understanding that he drops this cosmic brain term for the actual computation. But it seems here that you are keeping this cosmic brain. Am I understanding something wrong?
I forget exactly what he did, but ultimately it's the same.
Okay, thanks.
Okay, so let me move on with a few more examples. This is my last page. So one example, which is I guess related to the second to last question, was what if we apply this to a case where the branch cut does not hit the ADS boundary? So here's an example of computing the entropy of the Hawking radiation. So we have an interval that extends from some finite points in the Bath region and go all the way to infinity. And again, we can evaluate this using the replica trick. So you consider many copies, and then you allow for all possible gravity configurations and focus on the saddles. So one saddle is what happens here when I go to the right. It's the semi-classical saddle or the Hawking saddle. That's the case where each ADS region is individually filled with the hyperbolic black hole. Okay? So this will give you the Hawking answer, the one that has the ever-growing entropy as a function of real time. Or you can allow these different boundaries to be connected by a wormhole. This is what's going to give you the island saddle. Take, for example, the n equals 3 case. So I have just 3 copies. You can have a wormhole that looks something like this. Again, remember, I'm focusing just on replica symmetric configurations. And so this is what the picture looks like on the replicated manifold, if you will. And on the branch cut, this wormhole can be represented by this picture. So, so in terms of the branched cover, that's what I meant. What the wormhole here is represented by a branch cut in the gravity region. So if I go, if I go through this branch cut in this way, what I'm doing in this picture is that I'm going from this region down to that region. So these lines here are supposed to represent the branch cut. And the 2 endpoints here are the 2 endpoints there. And so we see how the island contribution comes about. And one more comment here is that the way that this calculation is set up in Euclidean space is by considering an interval in at t equals 0. Remember, if you recall, in the application of this formula to the black hole in Lorentzian space, I had to evolve the 2 endpoints in Lorentzian time, and you can do that here just by continuing these locations in Lorentzian time, and you'll get the same answers. You'll reproduce the formula in Lorentzian space. Good. And now the final example, which is much simpler, but also very surprising. Suppose you want to compute the entropy of the Hawking radiation, including the boundaries of ADS. So by that I mean starting from the boundary here, going all the way to infinity, and starting from the boundary here and going all the way to infinity. So the union of these two. Again, let's use our replica trick calculation. You consider many copies. Now notice, so when you do this, you notice that that this entire lower half is glued to the entire upper half of the second replica. So this setup here can be rearranged to look like the path integral on a single sheet with no branch cuts, all raised to the power of n. So it factorizes into a product of n path integrals, and you can fill in this gravity region subject to the boundary conditions. And it turns out that the only saddle here is just a disk, so you just get something like this. Remember, I'm only focusing on saddles, which implies that you have this factorization going on that I just described. So trace rho to the n is simply trace rho all to the n, which is just equal to 1. Therefore, we've derived that we've obtained this crazy result that the entropy of the radiation, including the ADS boundary, is equal to 0. So the state here, union there, is a pure state. So it seems that gravity is, well, we've already sort of sensed this, that gravity is really, really smart, and is telling us that you should think of this eternal black hole space-time coupled with the flat regions. You can think of it as somehow that it might have this dual description of some quantum mechanical system living on the two boundaries coupled to these half-space field theories. It somehow anticipates holography. So up to this point, we did not put in holography. Yes, we used it at various points just for intuition, but we never needed it. But we see that the gravitational path integral, just by its own structure, somehow it anticipates holography. So let me end on this point. Thank you.
Thank you, Ahmed. Okay, so are there any questions? Yeah, Arif, please go ahead.
Could you please elaborate on the last point? I kind of missed that. You said it anticipates holography because of.
Good. So because the entropy of, so we computed the entropy of the union of this region and this region. Clearly in the semi-classical limit, the entropy of this and this is not equal to 0, right? Because it's only a part of the global state. It's a subregion of the global state. There's quantum field theory entanglement naively between this region and this region and this region and this region, for example. But gravity tells us no, that's too naive. The entropy of the union of this and this is equal to 0. So the eternal black hole is a pure state only of this region and this region. Sorry, it's a pure state. I don't know why I said only, but it's a pure state of this combined region, and it tells us that, or maybe I should say it the other way, a different way. If you look at the maybe I should have written an equation. This tells us that the entropy of this union this is given by the entropy of the entire slice. Oh no, that's not that. That's actually confusing.
Maybe you're trying to give words to the factorization. Really, you're saying the internal Hilbert space and external Hilbert space are really the same thing, and that's why, I mean, the state outside completely is pure. So if you think of the full slice, then state inside is also pure. And is that what?
I would agree with everything you said except for the last sentence, that the state inside is pure. The state inside is not pure, but the state outside is pure. That just tells you that the inside is contained as part of the outside.
If you consider the full slice, and then think of that slice being divided into two parts, and then you're saying one part is completely pure by itself.
Mm-hmm.
And then does it not follow that the other part is also pure by itself?
Usually, yes. But if the Hilbert space factorizes in the way that you said, that it factorizes in terms of the inside tensor the outside, then what you said is completely correct. But what we're learning is that that's not actually what's going on.
Well, yeah, that's exactly what your point is, anticipating holography, because that would be like, because you're saying that inside is the same as outside, right?
Precisely.
Yeah, so that I fail to see that conclusion coming from something here, but
well, how about this? Suppose we assume holography. Okay, so if we assume holography, then we say that the entire that this entire system here can be re-expressed as something like this. Do you agree with that statement?
Yes.
If you can do this, then this result is not surprising. That the entropy of this region and this region is equal to 0, because that's all there is.
Right, exactly.
Boundary holographic system. that's really all I meant.
Okay. Thanks.
Ahmed, could you make some comments about the four-dimensional black hole? I mean, if we try to do the same computation for a four-dimensional black hole coupled to a small number of matter fields, do you expect to find the solutions of this type? I mean, for a realistic black hole.
Yes, I do.
Yeah, I had a similar meaning. Can you translate what you have learned from this 2D example to some kind of a scenario for four-dimensional black holes where, yeah, what would be your fantasy scenario for a four-dimensional black hole from this for information?
Is part of your question the worry that in 4 dimensions, say, I don't have a large number of matter fields, something like that? Or
that played a role in determining the solutions, right?
Correct. Although so let me first comment on that before I comment on 4 dimensions and so on. So let me see. Let me go back a few slides. So if you look at the situation here, so something that happens when you compute the entropy at late times is that the amount of entanglement between the island and the radiation is very large. That somehow it's that fact can sort of play the role of the large C that we use to find to find the saddle points. Even though I didn't talk about the large C much, but these saddle points really are, you should think of them in that limit. So somehow, so you can work with small c, but at late times in a configuration like this, where there's a large amount of entanglement, this large amount of entanglement plays the role. It's like a large kinematical factor, which makes the stress tensor of the matter the matter stress tensor sourcing the gravitational equations. It makes that large. It comes from the fact that there's a large amount of entanglement between the island and the radiation. Maybe
so you mean that you can probably still use a semi-classical approximation, even though you have a small number of fields backreacting.
Yes, exactly, in certain limits. That's right. And maybe let me also say a more physical way to see this is the fact that you have a small number of fields tells you that the location of the boundary of the island is kind of fuzzy. You sort of don't know exactly where it is. Let me go back one slide. So in this case here, we say that this X is somewhere outside the horizon. But if you work with a small number of fields, then it's actually just like a Planck distance away from the horizon rather than C times a Planck distance. And so it's not, you can't sort of distinguish exactly where this point is, whether it's on the horizon, outside the horizon, it's not clear. But in this case, at late times, even though this is fuzzy and this is fuzzy, at late times, the size of the island is huge. So the the ratio of the error of where this point is over the length of the island goes to 0 at late times. So that's like a different way of saying that the island is actually there. It's not a fiction. It's not well. It's there even for a small number of fields at late times.
Okay, thank you. So Pedro, you want to ask your question?
Yes. Could you go back to the last slide?
Or the very last slide.
Yeah, the very. Okay. I don't know if you can draw or not, but could you make at least a schematic thing of the real-time evolution of the drawing on the lower left? Because you said that yeah, that branched cover you could extend it to real time. Could you make at least a schematic drawing of that?
The only drawing I can do is, I don't think it's going to be that instructive, but you guys see this?
Yes.
Okay. The idea is that somehow somehow there's a, I'm guessing it's, somehow there's a, I don't know where to connect the second point. Should think of there being sort of two cuts here. Here, this is supposed to be a direction that is going outside of the board.
Okay.
And somehow you'll find that this guy also does that. So that the actual saddle point, you look at these points, you continue these points to some Lorentzian time, and then you'll find that the saddle point of where the island is also at some Lorentzian time.
Okay.
That's the only drawing I can draw for you now.
Okay, and mathematically you just extend tau to IT or something like that, and you end up with the correct expression.
Exactly. Tau goes to whatever. Tau goes to tau plus IT. So there's sort of two different times. There's the Euclidean time and there's a Lorentzian time.
Okay, thank you very much.
Mm-hmm.
So Joan has a somewhat long question. Joan, do you want to read it to say your question, to ask your question, or should I read it?
Yeah. So I was wondering if you can tell us something of the conformal welding problem, and I was wondering, for example, in the paper we reached the island by these new techniques coming from the replica trick, but can we imagine that this happening because of dynamics in the bulk theory, or dynamics that come from the boundary theory as we have to deform the Schwarzian action, like a real physical process that tells us that information is not lost, not only because the mathematical trick.
So let me make a few comments. So the first is, unfortunately, the status of this thing is that we understand it basically just as a trick.
Okay.
It's very mysterious. Why does gravity know about this result? Why does it know about the page curve? Maybe Douglas will have some more comments to say about this. Let me see. Yeah, and the other aspect is whether this sort of resolves the problem. I don't think it resolves the problem, but also, well, it sort of depends on what you mean by the problem or by the paradox and so on. So you can mean one of three things. One is to understand the microstates of the black hole. This does nothing of that. Two, that you know what you've sort of you've written down the S matrix of the black hole, the map between initial states and final states. That we only have partial information about that because if you throw something in, using this subregion duality and so on, you can read it off from the radiation. But that's also very partial, not complete. The third thing you can mean by the information paradox is just to reproduce the page curve, irrespective of how you do it. Just do a calculation, or rather find Hawking's mistake, and then just reproduce it. And in that sense, I would say that it's in that sense that we've made the most progress. I don't want to say we've completely resolved that for a reason I'm going to mention in a second. But if Hawking did this calculation and then just include back in the 70s and noticed that the wormhole reproduced the page curve, or gave you a curve for the entropy consistent with unitarity, then it would be there would not have been an information paradox. These first two questions that I mentioned, they would be still important questions for understanding black holes, but it wouldn't be a precise calculation that has a contradictory answer. However, even there, even maybe we should not be that optimistic about this, or should not completely buy into my description of this third point, because what's actually happened is that the information paradox has now been replaced by a wormhole paradox. These wormholes they're kind of weird. Douglas, maybe I think he mentioned this, or he might say more about it today, that these wormholes are somehow not consistent with having a single, so they're not consistent with this gravity theory being dual to a single unitary quantum system on the boundary, but they seem to say that you should have some sort of average of boundary quantum mechanical systems. But this sort of has some trouble because in higher dimensions, it's hard to define these ensembles of unitary quantum systems and so on. Maybe Douglas will have a few more points to say there. So I would say what's happened here is that the information problem, the entropic information problem, has been replaced by a understanding wormholes problem. So I hope that addressed your question.
Okay. Thank you. Okay.
Oh, so one last thing about dynamics. So something that might, if you only look at this from the Lorentzian picture, you can have the point of view that what's happening is that when you want to compute the entropy of the two regions in the bath, that as you evolve forwards in time, the thing that happens is that the gravity somehow wants to screen these twist fields in the bath region. And so you can give this phenomenon the interpretation of there being pair production of twist fields in the bulk that create the islands and so on. So there might be some dynamical story like that. I just wanted to throw out that comment.
Okay, thanks.
Okay, so we're running a bit late. So this is a good point to thank Ahmed for the very nice lectures. Thank you. And please do not disconnect. I think that this will say a few things.
Okay, Ahmed, yeah, okay, hi. Okay, maybe can all of you try to show themselves? Turn on your video. Thank you. No, so, one of the great things, can you hear me?
Yeah, I'm sorry, I wouldn't because my daughters are sleeping.
No, okay. Those who are in a presentable state, yeah, please reveal yourself. Okay, no, what I wanted to say is that one of the, what I remember from my attending spring school and also then coming here as a lecturer and so on in the past, and also going to other schools elsewhere, I think one of the most important aspects of going to schools is actually to meet your peers and make friendships and sort of find out who are the people interested in questions similar to what you are interested in. And that actually, unfortunately, is missing from this because of the particular format that we have and the very strange situations that we are in. So I just wanted to ask you, we, the organizers, we thought of different possibilities for improving the situation, and we couldn't quite agree upon what would be the best way to do it. I mean, first of all, it would be nice if we at least know who you are, what you're interested in, where you're from, things like that. Or maybe you can, yeah, so I just want to throw this out to you. Do you have some ideas that we can improve the social interaction among yourselves? Please feel free to contribute. For example, would you be willing to have Zoom sessions? Maybe 10 of you can have your private Zoom sessions and invite whoever is interested. You know, you can sort of say, okay, or maybe put out your information about yourself on the social Slack channel. Or we could have a session devoted to introductions. So everybody says 1 minute about themselves and we go through. Maybe we can divide this group into two breakout rooms, and in 45 minutes we can at least come to know about each other. So do you have any ideas about this, or do you want to, or do you think there is nothing we can do to improve this?
Can I comment something?
Please, please.
I was in a previous virtual meeting, I guess, or workshop. They use. I'm afraid I'm like making some advertisement here, but they use Remo, which I didn't know, and it was a different platform from Zoom, but it provided like tables and like a coffee break room, and you can chat distinctly with different people. At least for me, it ended up working. Maybe you could explore that. At least for me, it ended up working, and it was not.
Can you type it? How do you write it? RIMO?
Yeah. Yeah. Let me type it in the chat for everyone.
Okay. There is another platform called Jitsi that Pavel, for example, had tried. Remo, I see. So is it something on top of Zoom or is it independent of Zoom?
No, it's independent of Zoom. It's not equivalent to Zoom. It's like a big room that you enter. Unfortunately, you have to do like a username and stuff that it's quite.
So we cannot switch to it easily now. At this stage, we cannot switch to it.
No. It's a web page, but then you go to like a coffee break room, and you can see other people in the coffee break, and you can sit in the same table and like discuss, or maybe close the room, make a private discussion. It also provides a webcam, and it has a blackboard. But a similar experience to a coffee break, at least in this situation.
Okay, so maybe we can try this next time. It's probably we cannot try it at this time. But this
no, I guess for this time it's quite complicated. Yes.
Do you think it will help if, let's say, we have about 90 people maximum? If you split into, say, groups of 9 and 10 people, and maybe 10 of you can take some lead and invite. Will it help if you form 10 groups and then you arrange your own Zoom session independently? Or you think it's too awkward? It's too awkward.
Yeah. Nobody replying.
Okay. Do you think it will help if you have a introduction session or not particularly? Because there are too many people. I mean, so just going through mechanically through the introduction is not going to be useful. So
well, if not the introduction, maybe. I mean, we see there are a lot of people in the context of the courses that are provided, a lot of people with their own thinking about the topic or where it's coming from and where it's going to. If there are people who want to just say what kind of questions they have in their minds, and if somebody's interested, or what other kind of ideas they're looking at. So that's kind of thing that you would expect in a conference, and like in previous ICTP schools, instead of introducing, and that kind of builds up the conversation and exchange of ideas and interests. So, but that it's more volunteer based. Somebody who, if there are people, I don't know, many people asking questions, and you can tell specifically what they have in their minds or what kind of answers they're looking for. And so if they could just say it out loud, say, well, these talks, this is what I got, and these are kind of questions I have in my mind, or these kind of ideas, or what more can be done. So they could just, have a Zoom
Yeah,
session.
by introduction, that's what I had in mind, some kind of scientific introduction.
Yeah.
My name is this, I'm from this institute, and I'm interested in, say, black holes, or I'm interested in mock modular forms. And then people who have similar interests can maybe have a Zoom call together.
Yeah, I think that's a good idea. And this probably could already be, because this Slack that you put together, I think that's great to pose the questions and also to just initiate this kind of thinking instead of,
So can I
everybody do
suggest
what.
maybe that on Slack, why don't you give, maybe you can turn off yours, otherwise we'll get 100 notifications. So you can turn off the notifications from Slack, but maybe, let's see. I mean, if you can somehow form roughly 6 or 7 groups of interests, I'm interested in black holes, or I'm interested in mock modular forms, or I'm interested in entanglement entropy. If there are 5, if some of you can, why don't you just some of you start this, I think it should come spontaneously from the students. And I want you to take a bit of initiative that on the social media, maybe you should just, some of you, why don't you just say, okay, I'm interested in these topics. If anybody else is interested in this, why don't we have a Zoom call together? Something like that might work.
Yeah, that's a good idea. We can try to post that on the Slack and just see.
Yeah, so please try to use the, and if you want some of the speakers or tutors to be, to attend your thing, we can allocate one session next week for this kind of a social discussion. Social meaning it's kind of scientific social discussion.
Sure, yeah. Yeah, that's a good idea, yeah.
So please feel what I want to, first of all, I want to sort of break the ice a little bit. Nobody's using this social channel, use it, because this is the way you'll actually meet each other. And social channel is meant to be social, so you don't have to be very careful about your minus signs and so on. You can just say what you want. I'm interested in this. And or factors of 2 or something like that, and you just say, okay, I'm broadly interested in this, and I'm holding a Zoom call on such and such time, and you can post the Zoom link on the social media, something like that. Okay, that could be one idea we can try to do. Anything else? If you have some ideas, I don't know. Because that is really very important. I found in my experience, one of the most nicest things about going to schools was to meet new people and to make friendships. And sometimes they become your collaborators and you start some nice collaborations. And so you should somehow use this social channel to find like-minded people who might, you might just keep in touch with and be scientifically be interested in each other or something like that. So I just wanted to suggest that to you. If you have any other additional ideas, feel free to speak now. Or if you have some ideas, you can maybe post it on the social channel or on our Slack pages. Anybody else has any ideas? No? Okay, somebody has to start. Huh? So put up something on the social media, social channel. Few of you, I urge you to do it. Just say something about yourself and what kind of problems you're interested in. Okay, that's all we wanted to, we were thinking among ourselves, what can we do better? And it's,
okay.
I mean, we don't want to create something artificial. So if it comes out spontaneously from you, that's even better. So anyway, I will just give it back to Kyriakos.
Okay, thanks a lot, Atis. Yeah, okay. So we meet again in 1 hour and a half from now. Bye-bye.
Bye.
Thanks, Ahmed, for a nice talk, nice lectures.
Yeah, thanks for the invitation. It was a delight giving these talks.
Yes.
I also realized I didn't answer your question about 4 dimensions.
Yeah, I mean, I just want to know, yeah, how do you imagine the resolution to proceed? So what is the idea that once you cross the page curve, you will get... So first of all, I find it quite surprising that in a non-gravitational theory like the sun, you know, if you had to really figure out how the information actually comes out, the correlations, you would be really, it would be almost impossible for you to do it, because you would have to figure out some subtle correlations between late and early times, and you would never be able to do it. Somehow in a theory of gravity, you're saying that there are some effective saddle points that allow you to at least assert that the entropy is working out okay, even though you don't know the detailed mechanism. Is that somehow the idea?
Well, I mean, even for the sun to compute the entropies, I mean, you can do various approximations, and you just say you have, you know, thermal radiation or whatever, and so on. That's, I don't think you'd get an answer which is very far off from the actual answer when computing the entropy.
No, but wouldn't you will just get thermal radiation all the way, right? And to really see that page curve is turning down, you'll have to see that there are some correlations between very late radiation and early radiation, which that you will never be able to really calculate.
But even here, actually showing that there's correlation, like maybe the better thing to talk about is like the S matrix, for example. Let's think about the S matrix of the sun and the S matrix of the black hole. I think the black hole S matrix is more complicated than that of the sun.
But somehow your saddle points are able to give you some information. I think in the case of the sun, you have no way of really showing that the page curve turns down, right? That's the sort of our belief.
I see what you mean.
I mean, the fact that you're able to show it in kind of with a calculation, that already is quite surprising.
Well, no, maybe no. Let me. For the sun in 1+1 dimensions, it might actually be easy. So in higher dimensions, unless your field theory has some special features or properties, you won't be able to do this calculation, because the entropy of a region in a quantum field theory is something very hard to compute. Like it's only known, well, the examples I know are restricted to 2 dimensions for a single interval. As soon as you go, so CFT in 2 dimensions for a single interval. If you consider 2 intervals, it depends on the details of the theory. We don't know the answer in general. If you go to higher dimensions, even for a single interval, I don't think we know it unless it's like it's a holographic theory or something. So there are technical obstacles to extending the story to higher dimensions. But there are examples in higher dimensions where it does work, where you, for example, take your field theory to be a holographic theory and so on and so forth.
But sorry, just to maybe, isn't it, regarding this question, isn't it correct to say that these wormholes allow you to compute only the traces of powers of the density matrix and not the individual matrix elements? So you can only get some, some specific aspects of the radiation. You not the details.
Yeah, exactly.
Yes.
And sorry, I didn't understand. Why do you say that the sun is the radiation from the sun is different, qualitatively different? I mean,
it's not.
But by the sun, we mean a perfectly thermalized,
yeah,
mechanical system, which we're not.
Yeah, the
the
star
black hole.
completely evaporates. Yeah, if you take a sun which completely evaporates, then most of the time the radiation will look thermal.
Yeah, in what sense is it qualitatively different from the black hole? I mean, if you only look at the
No,
radiation
I
at
mean, if you
infinity.
believe that the black hole is unitary, then it should be qualitatively the same. But I'm saying that for the sun, you won't be able to really say whether, when the page curve turns down, right? I mean, we all believe that the page curve.
Yeah. No, I was because I think Ahmed made a comment that there's some qualitative difference, and
Okay, yeah, your question.
Well, it depends on yeah, I just realized that it's the same calculation for the black hole or for the sun. It involves computing the von Neumann entropy of some region that contains all the radiation that comes out of the black hole or the sun. The only difference, so before the page time, the entropy of the radiation is just the semi-classical entropy of the radiation. You just have the state outside, and you just compute the entropy of that region. For the sun, it's that calculation all the way through, from the beginning to the end. But for a black hole, for the first half or up to the page time, it's that calculation. But then after the page time, you need to include the island contribution. So in that sense, you can think of it as being more complicated in the sense that after the page time, while the sun calculation is the entropy of a single region, the black hole calculation after the page time, once you have the island, it's a union of disjoint regions. Or rather, it involves the entropy of a union of disjoint regions. So then it seems like it's more complicated in that sense.
Yeah, but on the other hand, you're able to get some notion of some averaged entropy by doing a fairly semi-classical calculation of some gravitational saddle points.
Yeah.
Which you would not be able to do for the sun. There is no analog of that.
That's correct.
So it's
Although, let me just correct something I just said. So I said that for the black hole, you need to compute the entropy of the union of two regions, the outside and the island. But really the entropy is going to be dominated not by the matter entanglement between these two regions, or rather the matter entanglement of these two regions, but rather by the area term coming from the boundary of the island. So in some sense, the black hole answer is easier.
No, that's what I'm saying. The black hole answer is easier, hugely easier, right? Because if you really try to reproduce the page curve of the sun, you wouldn't be able to do it.
That's right.
Whereas here you seem to have some handle on it because of some gravitational actions.
It's because the entropy is captured by an area.
Yeah, that's very interesting. Yeah. Okay, I guess you have given all the. Yeah, I should look at the papers to follow. They are all in your Slack.
I put up the references after every lecture, so I'm gonna put up the references for this lecture soon.
Okay. Okay, great. Thanks.
Yeah, thanks.
Unfortunately, I have a meeting in another 3 minutes. Another meeting on Skype.
Okay. Okay, thanks, guys.
Okay.
Sure,
See you
thanks.
later, Ahmed. So,
See you.
Bye.
bye, Tish.
Bye.
Hi, Kyriakos.
Hi, Douglas. Do you want to share your screen?
Yeah. Let me get that going. I think somebody else is showing a screen at the moment. Okay. Okay.
Douglas, can we start?
Sorry, but were you asking me?
Yeah.
Yeah.
Okay. All right. So then now we're moving on to the last lecture of the day, and we're very happy to have Douglas, who will give his last lecture on more on quantum black holes.
Okay, thank you. So last time we were computing the von Neumann entropy in the simple JT gravity plus brains model, and we were using the replica trick here. So that meant that we needed to compute trace of rho to the n for different values of n, and then somehow continue the answer very close to n equals 1. And the boundary conditions looked like this. N different boundary segments that could either have their own disconnected two-dimensional gravity spaces, like shown at left, or we could have something completely connected, some geometry that connects them all completely together. And last time what we did was we analytically continued each of these two extreme contributions in n to n close to 1. And we found these two answers. But actually, last time we were using an approximation to JT gravity where we keep only the topological term in the action, so only the S0 term, and we threw out the rest of the JT gravity action. In principle, what you should do is you should compute the full action of JT gravity on this kind of funny connected space here, and then analytically continue the answer in n. That sounds a little bit difficult. But still, we would like to do something like that in order to study this contribution of this geometry here in the full JT gravity theory. But we expect a simple answer. So we expect to get, instead of S0 here, we expect to get the entropy of the black hole, the Bekenstein-Hawking entropy, which is S0 plus a term involving the value of the dilaton at the horizon. So we expect to get a very simple answer. And so there should be a simple argument that gives it. And actually, there's a really beautiful argument that computes this thing. So don't worry about these diagrams for now. We'll get to them in a minute. But this is a really beautiful and important argument in black hole physics. And I'm going to show you a sort of simple special case of it here. And I really recommend that you read the explanation of this in the paper by Lukowitz and Maldacena. So they actually give two derivations of this. And I strongly recommend that you go through both of them. It's kind of a difficult argument to understand the first time. Even though it's simple, it's just a little bit slippery. So I'm going to try to show you the argument. And if this is the first time you've seen it, you might follow all the steps, but at the end, you might still feel like you didn't fully get it. And well, that's okay. So let's now proceed to the argument. So we're trying to compute this limit. Limit n goes to 1 over n minus 1, log trace rho to the n. So trace rho to the n is computed by some geometry like this pinwheel geometry. And log of that thing is like minus the action. So minus the action cancels against this minus sign here. So we just basically are computing the action of this geometry. Not quite though, we're computing the action of this geometry minus a normalization factor, which is the action of just trace rho itself. So what does that work out to? Well, okay, so we have limit n goes to 1. We have the same prefactor that we had before. That's just coming along for the ride at the moment. Then we need to compute the action of this space here, this big connected pinwheel. And then for the normalization factor, we need to subtract off n times the answer when n equals 1. So we have this connected geometry that depends non-trivially on n. And then the normalization factor is just some very simple dependence on n, this geometry here. So we need to evaluate these two actions and take the limit n goes to 1. Okay, so the first step in the trick is the following observation. I can take this geometry here with n different boundaries, and I can cut it up into n pieces that are the n pieces. So each piece is like the Zn quotient of this geometry. It has a Zn symmetry, and if I study the Zn quotient, I'll get a piece that looks like this here. And so naively, the action of this full geometry is just n times the action of one of these pieces. So that's why I have put a factor of n outside, and now we're just studying the action of one of these pieces. Notice that the second term, the n comes out front, and we're just left with this piece. Okay, but this makes a small mistake. The small mistake is that in the full geometry here, the original geometry we're trying to compute, there's no conical singularity at the center of the diagram. At the Zn fixed point, there's no conical singularity. But after we take the quotient, then there's a conical singularity. And the right rule to evaluate the action of the big smooth space is that you should not include the contribution from the conical singularity. So the gravity action is local, so the computation is correct everywhere away from the singularity if we just multiply the quotient by n, but it's not correct at the tip. So to fix that mistake, we should subtract off the contribution from the tip itself, from the tip of this cone. So maybe I should have mentioned this earlier, the dotted lines here should be identified. So this geometry here, you identify the two dotted lines, and then you get something like a cone with a conical singularity at the tip. And the correct procedure is to compute the action of that space and then subtract off the contribution of just the tip itself. Okay. Now, that was the first step in this sort of slippery trick. There's one other tricky step, and that's the following. We're now interested in this answer for n very close to 1. And let's look at the first. So in the next line, I've drawn something where n is sort of close to 1. So you can see that the opening angle of this cone becomes close to 2 pi. So the first term inside the brackets and the third term inside the brackets look quite similar to each other. The only difference is that there's a small conical singularity in the center of the first one. Okay. Now, okay, here's the tricky part. The first one and the third one differ by a small variation, inserting this conical angle. And it's a variation of size of order n minus 1. So it's a first order variation in the parameter n minus 1. Because the angle here is different from 2 pi by an amount proportional to n minus 1. But the action of this configuration, if we make a small variation, is 0. The change is 0 at first order in any variation because it's a classical solution. The condition that you have a classical solution is that the first order variation of the action is 0. So you can change this geometry in any way, and to first order, the action will be 0. Here, we're changing it in one particular way. We're adding a small conical singularity. And because we started with the classical solution, that means the first order variation in the action will be 0. So to first order an n minus 1, this term here cancels against the first term. The first and the third terms cancel at 0th order and first order in n-1. So that means that they can give a non-zero contribution at second order in n-1, but because we're taking the limit n goes to 1 and only dividing by 1 power of n-1, that will vanish. So for the purposes of computing the limit n goes to 1, the first term and the third term are equal to each other and they cancel each other out. Okay. So all that remains is just the contribution from this tip, this small mistake that we made, this conical singularity contribution. That's all that remains from this computation. And so this big, elaborate, complicated geometry has canceled out. All of the complicated stuff has canceled out, and all that we're left with is the contribution from the conical singularity at the tip. Okay, so we've simplified the computation a lot to just this contribution here. And that's the main conceptual part of this. The final step is just a little bit of simple bookkeeping. We need to actually compute the action that we get from this conical singularity. This part is easy. All the hard stuff is in this kind of subtle argument that went before. Okay, so now let's do the easy part. So I claim that if there's a conical singularity at the tip of some cone, let's say it's at the origin, then square root of g times r, the scalar curvature, will have a delta function singularity at that location. And what we would like to do is compute the coefficient alpha as a function of the angle of the conical singularity. So very, very close to the tip, we can approximate this space by a part of a flat cone. The curvature of the background space is unimportant. It's just a flat cone. And to compute this coefficient, we can use the Gauss-Bonnet theorem. That says that the Euler characteristic of the space, which is 1 because it's topologically a disk, is given by this Gauss-Bonnet integrand. So it's a flat cone, so away from the tip, the curvature is 0. So the only contribution from the first term comes from the tip itself. And if we plug in this formula here, we get alpha divided by 4 pi. Okay. The second term does get a contribution from the extrinsic curvature of the boundary. And it should be proportional to the length of the boundary, which is proportional to theta, the total opening angle of the cone. And you can get the coefficient 1 over 2 pi from the observation that when we have no conical singularity, theta should be 2 pi. So if we have a full cone with no singularity at the tip, then theta is 2 pi, and that fixes this coefficient. So we find 1 is equal to this expression, and we can solve that for alpha as a function of theta. Okay. We plug that expression for alpha in here, and we find that square root of g times r is determined by the opening angle of the cone in this way. There's a singularity proportional to this. Okay, and if I plug in the dependence of theta on n, the number of replicas, then for n close to 1, I found this simple expression. Notice that if n is equal to 1, then we have no conical singularity at all, and the curvature vanishes, as it should. Okay, so now we can plug this into this limit, n goes to 1. We find this limit of square root of gr is equal to minus 4 pi times the delta function. So when we compute the limit of this conical defect, what we do is we just replace square root of gr everywhere in the action by 4 pi times the delta function. And using the JT gravity action and making that substitution, well, we replace this term here by 4 pi times the delta function, the 4 pi cancels the 4 pi out front, and we get the S naught, okay? That was a term we already computed in the topological theory. The main point of going through this is to see what happens to the second term. When we replace square root of g times r by 4 pi times the delta function here, we get 2 pi times the value of phi at the conical singularity, at the tip. And that's the horizon in the limit n goes to 1. So we get S naught plus 2 pi times the dilaton at the tip. And that is in fact the entropy for the formula for the black hole entropy that we discussed last time. Okay, so that's the end of that, that argument. We're going to move on to something else next, but let me see if there are any questions about this.
Himanshu, do you want to go ahead?
Yes. So I wanted to ask, like in the previous slide, you said that we are supposed to identify the edges of the cone. I don't understand why you are supposed to identify these edges, because I thought that you're supposed to like you have n of these and you're supposed to identify the edges of one cone with the edge of the next cone.
Okay. Yeah, perfect. I'm very glad you asked the question. Thank you very much. So what is the reason for this? The reason is not that when we identify these together, we literally get that geometry. It's that we get something with the same action up to a small mistake. So the action of gravity is local. So it doesn't care about these identifications, the pattern of identifications. It only cares about the bulk geometry. And the bulk geometry of this quotient here will be the same as the bulk geometry that we have here. The only difference will be that when we identify these dotted lines like this, we get conical singularities. And we have to fix that mistake by subtracting this term here. Does that answer the question, or?
Yes, it does. Yeah, thanks.
Okay. Yeah, that's a good question. That's one of the subtle points here.
Then there's a question by Gabriel.
Hi. I don't understand where is theta in the third line of the equation, in the third picture. Yes, there.
Okay. Good. So theta is the angle between going around this direction, between the dotted lines going around here. So
yes, but for n near 1, theta must be not greater than the previous one.
Yeah, so theta is a little bit less than 1. The theta is a little bit less than 2 pi. The formula for theta is 2 pi divided by n.
Oh.
So in this geometry, n is close to 1. Yeah.
I was supposing the opposite, because of in the middle picture, if I compare it with the first one, I think that for n greater, theta must be closer to 0. I am not understanding it in the right way, surely.
Let's look at this diagram up here, the top diagram. And imagine cutting it into n pieces. So we cut along here and along here to get one of those pieces. So that's what's drawn in the beginning of the second line. And let's compute the angle between the dotted lines there. When we put n of these pieces together, we get the diagram at top, on the top. And so when we put n of those pieces together, we must get angle 2 pi. That means that the angle of any one of those pieces should be 2 pi divided by n. So when n is bigger than 1, like
you're right. Thank you. Thank you. Yeah. Okay. Thank you.
Okay.
There is a question by Hamid.
Sorry, on the next slide, the contribution, the last contribution from square root g times 2 phi, that is not, that doesn't have a contribution?
Right. So that doesn't have any contribution from a very, very small region, very close to the tip. So this piece here is just some tiny region very close to the tip. And in a very tiny region, very close to the tip, square root of g times phi is basically 0, because it's a very small region. So the integral of square root of g is very small. The only term that can contribute is a term where there's some singularity at the tip.
Right.
And that's the term involving the curvature r.
Sorry, can you please repeat your answer to Himanshu's question, the question and the answer?
Yeah. So in principle, we're trying to compute the action of this geometry here. let's compare the action of this geometry to the action of n times its Zn quotient. So away from the tip, away from the fixed point of the quotient, those two spaces they're locally the same. And we have the same total amount of, if we take n times the quotient here, we have the same total amount as that. So the part of the action integral that's away from the tip will be the same in the two computations. The only difference is that in the second one, in n times the quotient, we'll have a conical singularity. And it's a fictitious conical singularity because it doesn't exist in the original geometry. So we have to correct for that by subtracting off this. There are other ways of saying it that appeal more and less to different people. So Lukowicz and Maldacena give two different arguments. And I think everybody has to find their own favorite argument for this. Okay, any other questions on this, or should we move on?
I don't see any questions.
Okay, so let's move on. So the rest of the lecture, we're going to go through a sort of long calculation. I know what we did already feels like that, but it's kind of hard to follow the details passively. So what I'm going to do is I'm not going to take a short break today. Instead, what we're going to do is pause at a couple of different points, and I'm going to ask you to think through some particular step in real time. So please be ready for that. So what are we going to do? In the rest of the lecture, we're going to take a step back and keep only the topological part of the JT gravity action. So we're going to ignore the r plus 2 times phi term and only keep the topological S0 term. But what we're going to do is we're going to compute the contribution from geometries that are intermediate between these. So far we studied very carefully the continuation of this completely connected geometry. And we also studied the contribution of this thing, completely disconnected. But what we would like to do is sum up all geometries that have intermediate degrees of connectivity and see how to analytically continue the entire sum. So let me remind you the following features. Let's start with the completely disconnected geometry and try to assess how big its contribution is. So there was the index of the end of the world brane, the index carried by the end of the world brane, and it runs over k values. And one of the things we have to do is evaluate the number of powers of k. In this geometry here, you can see that the dashed line, which carries that index, has just one loop. So when we sum over the value of the index, we get one factor of k. But we have n disconnected disk-like geometries, these gray regions. So the topological term gives a contribution e to the n times S0. So that's the first contribution. In the second one, at the very other end, we have n different index loops. So we have k to the n, but we just have one connected geometry. So we get e to the S0. And you'll notice that the total number of powers of k and e to the S0 in these two expressions is the same. It's n plus 1. And there are other geometries in between that have the same number of total powers. And what we would like to do is sum up all of those terms. So just to say it more explicitly, these will be terms that give contributions of the form k to the m times e to the m prime S0. So different powers here, where the sum of the two powers is equal to n plus 1. The two contributions we drew before are of that type, and there are also other ones of that type. So we're going to take a limit where e to the S0 and k are both very large, but they have some fixed but arbitrary ratio. And in that type of a limit, we'll need to keep all terms of this type. So, for example, a geometry that we'll need to include in the case where n is equal to 6 is this one left here. Let's just check that. How many index loops are there? There's one here, one there, and two here. So we get k to the 4th. And what is the Euler characteristic? Well, there are 3 disk-like regions, so we get e to the 3s0. So the sum of these 2 powers is 7, which is n plus 1. So indeed, this is a term that we need to keep. However, these other 2 terms we do not need to keep, because this middle one here, it has the same number of index loops, but because we've added a handle, the Euler characteristic decreases by 2. So we get a smaller answer. Similarly to the one on the right, it has the same Euler characteristic, e to the 3. But if you work it out, the number of index loops is just 2. So again, it's a smaller answer. So the leading diagrams that we need to sum, the ones that have the highest total power of k and e to the s0, are diagrams that have no crossings between the geometries like this. So we don't allow crossings, and no extra handles. Okay. So these diagrams give the answer for trace rho to the n. So for example, last time, one of the things we studied very early on was trace rho squared. And there were 2 different diagrams that contributed, a disconnected one and a connected one. And they gave these answers here. K e to the 2s0 for the one at left, because there's 1 index loop and 2 disks. And k squared e to the s0 for the one at the right, because there's 2 index loops and 1 topological disk. So similarly, we can compute the answer for trace rho cubed. There's 2 extreme contributions that I've drawn here, which give these 2 answers. And then there's something missing in the dots. And what I'd like to do is pause for like a minute and a half and let you guys work out what's missing there and what its contributions would be. So if you have worked out the answer, maybe you could raise your hand in Zoom and I see one person, but let me wait a minute until I see more people who have worked out the answer. I'm going to wait until I see at least 10 hands. Okay, well, that looks good. Now, could one of you just shout out the answer? I don't want to call on somebody and put them on the spot.
I think in addition to those 2 contributions, there's 3 times k squared to at e to the 2s0.
Okay, great. That's also what I found. And could you describe the configuration that gives that?
So just connecting 2 out of the 3 regions on the boundary.
Beautiful. So you take
to do that.
a geometry like this, you leave one by itself, and then you connect the other 2, and there are 3 ways of doing that. Perfect. So that's indeed the answer for trace rho cubed. This gets more complicated if we increase the value of n, And but somehow we're supposed to get the exact answer and then analytically continue it in n. And this seems sort of hard. We could pursue this, and I could wait longer for you guys to raise your hands, and we could do n equals 17. So we could do some particular integer n, but that wouldn't help us actually compute the analytic continuation as n goes to 1. Somehow we need a formula that allows us to continue the answer in n, not just compute it for some particular value of n.
Sorry, Douglas. There was a question by Aranya. In each of the disconnected parts, the Lorentzian version had island parts. How do we understand the island in the connected geometry?
Okay, the island is actually comes from this connected geometry. That's where the island comes from. So the fixed point, the boundary of the island is the fixed point of the Zn symmetry. So it's this black dot here, and that's where the island contribution comes from. The trivial contribution with no island comes from the continuation of the disconnected geometry. Okay. But okay, so we need to try to figure out how to compute this in a way where we can continue it in n. And here's the key technical tool. I'm going to explain the tool, and then we're going to compute it, and then we'll see why it helps. So at the moment, I'm just introducing something kind of random, and I'll show you later why it's helpful. So we define this thing called a resolvent. This is a very common quantity to study in the theory of random matrices. And what we're studying has some relation to that, but it won't be too important. Anyhow, what the resolvent is it's a power series in rho to the n, where each power is divided by a different factor of lambda, 1 over lambda to the n plus 1. So actually, you can think of this as the inverse of lambda minus rho. And graphically, this resolvent is the following. So for the resolvent, we write this symbol r with the 2 dashed lines representing the 2 indices, I and j. And it's given by the following boundary conditions. The term n equals 0 is just 1 over lambda times delta ij. So that's this term here, where we have to remember that the dashed line comes with a factor of 1 over lambda. Then the term n equals 1, we have 1 over lambda squared times rho. So we have 2 dashed lines with 1 over lambda each, and then we have rho, where rho is determined by this black, the boundary conditions for rho, as we've seen, are this interval of asymptotic boundary, the black line. And similarly, we have contributions with more copies of rho. So the sum of the planar geometries, the non-crossing geometries, are ones that look like this. We need to fill in these boundary conditions with geometry. In the first diagram, there's nothing to fill in, so we're done. In the second term, we have to fill in one asymptotic boundary, and there's only one way of doing that. We just fill it in with a disk. The second term, we have 2 different asymptotic boundaries, and we can either have a disconnected contribution or a connected contribution, and so on and so forth. Now there's a trick for computing the resolvent, which is the following trick. It's like a Feynman diagram trick that you use to sum up a series of Feynman diagrams. And it's based on the following recursive relation for the sum of all of these diagrams. And the way that you can see why this relation is correct is the following. Any term that appears in the resolvent, in the second line here, any term that appears here, examine the first black asymptotic boundary. It will have some geometry attached to it. And it might be disconnected. If it's disconnected, then the sum over everything that follows will be given by this term here. Disconnected plus the sum of all diagrams. But it might not be disconnected. And if it's not disconnected, then it might connect up any other place along this sum of diagrams. It might connect to one other location, as is shown here. or it might connect to 2 other locations, as is shown here, or 3. And in between the places where it connects, we have a sum over all diagrams given by the resolvent. So this is a recursion relation for the resolvent. A self-consistency equation for the resolvent. So to write that in a concrete formula, it's helpful to define R as the trace of the resolvent. So a sum over I of RII. We'll use that in a moment. So let's try to write this equation out explicitly. So the first term, so the left side is Rij, and the first term on the right-hand side is Kronecker delta ij divided by lambda, because remember that dashed lines come with a factor of 1 over lambda. Okay. Now let's look at the second term. We have 1 extra dashed line at the left, giving us a factor of 1 over lambda. We have 1 disk-like geometry, giving us a factor of e to the s naught. Then we have the normalization factor for this geometry, which is 1 over k e to the s naught. So the contribution of this thing here is like e to the s naught divided by k e to the s naught. And then we have the resolvent itself. So that's the second term. Let's look at the third term. We still have 1 loose, 1 extra dashed line giving us a 1 over lambda. The gray blob here gives us an e to the s naught because it's topologically a disk. We have 2 asymptotic boundaries, so we have 2 normalization factors. And then we have 2 factors of the resolvent. The first one here is traced over. So that gives us R, the trace of the resolvent. And the second one is has its indices open, ij. So if we take the trace of this equation, we get R is equal to k over lambda, where the k comes from the trace of the Kronecker delta. And then we get the same expression here, just with Rij replaced by trace of R. And the same expression here, but with Rij replaced by the trace of R. So this is the equation that we get in the first 3 orders. So what I want you to do, and I'll give you 3 minutes this time, is to write the general term in this sum, in this series, and then do the sum of the series. You should find like a geometric series, and then write the equation that you get for R. Okay, and if you finish the calculation, or please just raise your hand again. Okay, this one was a little harder, so I only see a few hands, but what you should have found is that the general term in this series is you just take this expression r over k e to the s naught and raise it to the nth power. So here we have it to the first power, here we have it to the second power, and you get it to the nth power. And you can sum over those using the geometric series. So you get some simple expression by doing that sum. And if you simplify the equation a little bit, you get this quadratic equation. So this Feynman diagram identity for geometries gives us this quadratic equation for r. And we can solve this equation to get r. There will be some expression with a square root. I'm not going to write it for you because it's a little bit messy, but you can certainly imagine what it will look like. And we should think of this as giving the answer for r as a function of lambda, some formula with a square root. And because of that square root, the function r of lambda has a branch cut. And in the complex lambda plane, the structure of r of lambda looks like this. There's a branch cut extending like shown here with branch points along the positive real axis. That's important. The two branch points are along the positive real axis of lambda. So that's what the solution for the resolvent is. And this is a pretty cool calculation, I think, that you can do this sum over all these diagrams using like a Feynman diagram trick. So now what are we supposed to use R for? So far we just computed it. I told you what it was and we computed it, but for apparently no good reason. What can we do with it? So what we can do is use it to find a good continuation of trace row to the n for non-integer values of n. So let me remind you, the definition of the resolvent after we trace it is equal to this series, trace row to the n, divided by lambda to the n plus 1. So it's a type of generating function for all powers of trace of all traces of all powers of row. And if you start with this expression and you do a contour integral over lambda, around lambda equals infinity, with the insertion of lambda to the n, then you'll just pick out one term in this sum. You'll pick out the term trace row to the n. So we get a formula trace row to the n is equal to a contour integral around infinity of the function that we just computed times lambda to the n. So that's one way that you can compute this answer for any value of n. Okay, so the final little participation challenge is I want you to think about what is the problem with trying to use this formula directly to give a continuation in n. So here n appears as a parameter. Does that mean that in this formula we can use that to give the answer for fractional powers of n or arbitrary values of n? And you should find that the answer is no, but I want you to think of what the problem is. And can you think of some way to avoid that problem? Okay, 1 minute.
Sorry, I have a quick question before that.
Okay.
Do you mean around lambda equals 0?
No, I mean lambda equals infinity. Okay, can somebody volunteer an answer for why we can't use this formula to continue in n?
you get a branch cut, no, at the origin from the lambda to the n.
Yeah.
Right. So there's there's a branch cut. The function lambda to the n has a branch cut extending from the origin to infinity.
That's right.
So it wouldn't make sense to do a contour integral like this around infinity. It also wouldn't make sense to do a contour integral like this around the origin. Despite what I said, we could have done a contour integral around the origin. I like infinity better, but we could have done the origin. So I apologize for that. But either way, there's a branch point of this function. And so if we take, sorry, there's a branch point of this function if n is not an integer. If n is an integer, then there's no branch point there. But if n is not an integer, there's a branch point and we can't do the integral. So did anybody think of a way to avoid the problem?
We can change the contour so as to like go around the branch cut.
Ah, the branch cut in what function?
In R of lambda.
Beautiful. Okay, exactly. So, so this is the problem, and a solution is the following. So first, let's take integer values of n. So then that formula makes sense, but we can deform the contour. It's used to go around infinity or around the origin, and we can deform the contour so that instead it goes around the branch cut of R of lambda. So that's an allowed contour deformation when n is an integer. But now, after we do that contour deformation, we can continue in n, because now notice that the contour here does not surround a branch point of lambda to the n. So a way to make it totally clear is you can imagine shrinking this contour so that it goes right around this branch cut, so that it picks up the discontinuity across the branch cut, but everywhere along the integral, lambda is positive, real and positive. And if you're doing an integral of something real and positive to the power n, there's absolutely no problem with continuing n to arbitrary values. So let's now do that in equations. We were trying to compute the von Neumann entropy using this replica trick formula. And we've argued that we can replace trace of rho to the n by this contour integral around the branch cut with lambda to the n. So then we can just take this limit inside the integral, limit n goes to 1 of the lambda to the n. And if you evaluate this limit, you get lambda times log lambda. So the answer for the entropy is the integral around the cut of the resolvent times minus lambda log lambda. And this should look familiar to you. This lambda log lambda is the same formula that appears in the definition of the von Neumann entropy. And we can think about this whole thing as saying that the density of eigenvalues of the matrix rho R is given by the discontinuity of the resolvent across the cut. This is a very common thing in random matrix theory. You define a resolvent in the same way that we've defined it, and then you compute the density of eigenvalues by taking the discontinuity of the resolvent across the real axis. So if you start with that square root formula that we didn't write, and you compute the discontinuity across the real axis, you get the density of eigenvalues of rho R. That's sometimes called the entanglement spectrum. And given that function, you can now compute the von Neumann entropy with minus lambda log lambda. Okay. So that's the end of the long calculation. The rest of it, to take it to the finish line, is just to put in this formula with the square root and do the integral. And you find a function that looks like this. It smooths out, well, okay, so what are we plotting? The y-axis is the von Neumann entropy, and the x-axis is log of k minus s naught. So if log of k is much smaller than s naught, then we're over here, and the answer is basically linear in log k. It's just log k. But if the log k is much bigger than s naught, then it's basically, the answer is s naught. So this function that we found smooths out the transition between log k and s naught that we expected from the holographic entropy formula from the island rule. So from that rule, we expected to find this function, minimum of log k and s naught. And by doing this complicated sum over geometries with intermediate degree of connection, we were able to smooth out that curve and find this answer. So we did this today in just the topological approximation to JT gravity. But if you do it in full JT gravity, you find a sort of similar curve, the same method it works. Okay, so that's all we have. And since this is the last lecture, let me thank you for your attention throughout the course and for all of the really interesting questions. Thank you very much.
Thank you, Douglas. Very nice. So there is one question that I did not read earlier, which is it's about these intermediate diagrams. Can we think of them somehow as the evaporating black hole?
Well, no, I don't think so. I think what the intermediate diagrams represent is some kind of information about the density matrix of the black hole. But you have to compute something kind of subtle in order to see those intermediate diagrams. For most purposes, the completely disconnected diagram is the important thing. For the entropy computation, it can either be the completely disconnected or the completely connected one. And to get the intermediate diagrams to show up, you have to compute something kind of very close to the transition. You have to compute something very close to here. And so all those intermediate diagrams are giving us this smooth curve here. But it's, I don't know, it's, you might say it's sort of not that important compared to the completely disconnected or completely connected diagrams.
Okay, then Joanne has a question. Please go ahead.
Yeah, so I was wondering if it is useful, for example, to think on timescales here of this lecture to the timescales that we were studying, for example, for the spectral form factor. For example, we here are definitely getting information of the partition function of seed, and the form factor is basically calculating. I mean, we need to calculate that. So this contribution of the replica wormholes, for example, are maybe responsible for the behavior of the spectral form factor, or what you told us, for example, about what geometry should we include. I mean, is the page time? I mean, does the page time have anything to do in the discussions of the spectral form factor, or it's not related?
Okay, it's related in a sense. So in both cases, we have some disconnected answer and some connected answer. And as a function of time, one of them might dominate or the other might dominate. And in both cases, the contribution of the connected answer is suppressed by this topological term. So it's smaller by 2 factors of e to the s naught. Well, actually that depends. Let me consider, well, it's simpler to consider a case where the wormholes are, where we don't have the end of the world brains, and then that's true. Let me suppress a small detail in answering your question and say that they're both suppressed by basically the same factor, e to the minus 2 s naught. But they can be enhanced and they can dominate at late times. And the reason for the enhancement is different in the 2 cases. And so the times when the connected geometry starts to dominate is different in the 2 cases. But the basic suppression and the qualitative topological features are sort of the same.
Okay, thanks.
In both cases, actually, the main thing that happens is that the connected answer gets suppressed as a function of time. So the cylinder answer doesn't get as suppressed and the connected answer gets suppressed. So the connected answer starts out very big, the disconnected answer starts out very small, but then the connected answer decreases in time and eventually the disconnected answer can win. The connected answer can win.
And is there a reason why we use the word wormhole wormholes many times? I mean, are the wormholes here related to the double trumpet geometry, or is just to express some connection in the manifold?
Well,
or
yeah,
do I have to think on something else?
They are related. So they're related, first of all, topologically. A wormhole is a geometry that connects together these disconnected asymptotic regions. So by that definition, they're wormholes. But they're also related geometrically. And I didn't have time to explain that. But the actual geometry that you get of the replica wormhole is similar to the geometry that you get for the spectral form factor.
Okay. Thanks.
Douglas, can I ask a question?
Yeah, please.
Yes, Atish, please.
So, Douglas, could you give a kind of a 5-minute global summary of, meaning you started with some puzzles in the beginning of the lecture. So what part of it is resolved, and how it is resolved, and what you think are the lessons that generalize to higher dimensions?
Okay, good. Let me try to do that. So first of all, I viewed my role here as sort of a supporting role, trying to give some different perspectives and details on the main event, which was Ahmed's lectures. So mainly what we were doing was examining some of the problems and paradoxes that Ahmed presented in the simple context of JT gravity. So there were two problems that we discussed, basically two different qualitative problems. In the first two lectures, we talked about something called Maldasena's version of the black hole information problem. And that problem is a tension between the underlying discreteness of a quantum system and the fact that computations in black holes just seem to thermalize and decay forever. So there was some tension there. In the second part of the course, in the last two lectures, we discussed a related problem, which is the entropy problem for a black hole, or the bag of gold problem, which says that you seem to be able to fill a black hole up with too much entropy. Now, we discussed, so the main thing that we discussed in terms of trying to solve these problems were different topologies in the gravity path integral. So we have some problems with the lining up our gravity calculations with quantum mechanics. Quantum mechanics says the answer should be something, the gravity computations give something else. And so what we tried to do was to include other topologies in the gravity calculation. So for the problem discussed in the first half, for Maldasena's version of the black hole information problem, these other topologies do give a large correction, and they sort of stop the thermalization. But the answer that you get is a smooth curve for the spectral form factor. It's not the erratic curve that you expect for a particular quantum system. So we haven't solved the problem. We haven't found the discreteness of quantum mechanics. We found some kind of averaged theory of the discreteness, and that's different. In the second lecture, in the second part of the talk, we also used wormholes, the same kind of topologies, and we applied them to the entropy problem. And there, well, they also made a big change. And this time we don't have any problem with the change they made, because we were expecting to get a smooth curve. When you compute the entropy, you don't expect to get some kind of erratic function. You expect to get a fairly smooth function of time. And these wormholes give you some smooth function, so there's no problem in comparing the answer to what you expected in quantum mechanics. Now, you could ask, how much of the black hole information problem does that solve? Like, what do we know now about quantum black holes? How much do we know? And I feel that in both cases, what's happening is that wormholes are correctly describing some kind of average of the underlying quantum discreteness. And for the entropy computation, an average theory of that discreteness is good enough to give you basically the right answer. For the spectral form factor, for Maldasena's version of the black hole information problem, an average theory is not good enough. And so we're kind of happy with the answer that we got for the entropy, but we're not so happy for the spectral form factor. Now, I think the fact that we're not happy in one of those cases means that we haven't solved the problem. We have not understood the fundamental underlying discreteness of the black hole. So the fact that we can compute the entropy doesn't mean that we understand the quantum microstates of the black hole. So we have more work to do to understand that problem. That's the main thing. I feel the main summary.
Mm-hmm. And okay, so and does this address the firewall paradox in that? I mean, is the information inside is somehow stored in the outside in some kind
Yeah. So the relation to the Sorry, finish your.
Yeah. So yeah, what do you say about? What do we learn about that point of view, that the information?
Well, so I think the fireball paradox is not resolved because we don't have a microscopic theory of the black hole. So we don't know for sure that what we're doing here is representative of a theory where there's really microstates. But we can ask what the resolution looks like in this context of like an average theory of microstates. And it seems like the answer is that the region behind the horizon of the black hole is encoded in the radiation. I think this is something that Ahmed discussed more in his lectures, and I didn't have time to talk about that too much, but it's okay because Ahmed discussed it. So the fireball paradox was, one of the assumptions of the fireball paradox is that the region behind the horizon of the black hole is described by the degrees of freedom of the black hole itself. So it's described by the degrees of freedom that make up the black hole entropy. And the island formula says that the region behind the horizon is actually described by the radiation. And if you believe that, then you no longer have the fireball paradox. So it's, in that context, it gives a satisfying answer to the paradox, but one would like to have an understanding of this island formula in a case where we really have microstates for the black hole.
Actually, maybe I can ask Kyriakos, how does it relate to Papadodimas Raju?
Well, I think, I guess I don't know if Douglas would agree that if we try to reconstruct the interior operators using the radiation, as you just said, they may exhibit state dependence, which is perhaps somewhat unusual. So I don't know if you agree with this statement.
Yes, I agree with that, and
which seems to be an important ingredient in the resolution of this of the paradox. So
yeah, so Kyriakos and Suvrat realized early on that one of the assumptions of the fireball paradox was, well, that you could avoid one of the key assumptions by saying that the operators that describe the interior are state dependent. And the island formula seems to use that loophole. So it uses the state dependent loophole that Kyriakos and Suvrat pointed out.
Mm-hmm.
Yeah, in fact, I wanted to ask you something which was related to this end of the world brains that you introduced in the beginning. And as we discussed back then, they represent states which are not static. I mean, they're not equilibrium states, but we could imagine superimposing many of them to generate a typical state, right? Do you have any guess about the Penrose diagram, the space-time geometry for that situation?
Unfortunately, no, I don't. I've been bothered by this for a long time, and I don't know. One possibility. Okay.
Can you repeat the question, please? Sorry.
Yeah, so Douglas had this diagram a couple of lectures ago where there was this end of the world brain on the left side of the Penrose diagram, and otherwise the geometry was smooth. It had a smooth horizon, and quantum mechanically that diagram corresponds to states which are not approximately time independent. They're time dependent states, so they're superpositions of energy eigenstates with a significant width in energy. But you could, and each one of them seem to have a smooth horizon. So naively, you would think that by superimposing many of those, you can write down what we would call a typical state, a time-independent state. And the question is, what would be the space-time geometry of that state? Would that be a geometry with a smooth horizon? And if the geometry has the killing isometry that you would expect from time independence, then the only possible guess would be the Schwarzschild geometry. But the question is, how is it extended behind the horizon?
It's a very important question.
I mean, so is one way to formulate it. So you are saying that what is the Kruskal diagram of the Schwarzschild geometry replaced by? Is that
for a typical state? Yes.
For a typical state.
Maybe we have a little bit more time. There are a few raised hands. Could we try to answer a couple of questions, Douglas?
Okay, sure.
Yeah, so I'm not sure if this is the correct order. The order I say it is Hamid is first.
My first question is about in this calculation, you did not consider the contribution from the dilaton, just the topological term. If you consider that, well, what happens? And then the second question is that how far can one go continue this semi-classical computation and perhaps make it better?
Okay, good. So let me first answer the first part of your question. I think you were asking, with this whole resolvent trick and the Feynman diagram identity and so on, what happens if we include the JT gravity part of the action with the dilaton? Is that right? Yeah. So the calculation becomes harder, technically harder, but conceptually it's the same. The same trick works. The same equation can be written down. The main difference is that the solution is not just the square root formula. It's a more complicated function, r of lambda, but it has a branch cut in kind of the same place, and the method works the same. And the equation is more complicated, but it can be solved numerically, and you get a plot that looks sort of similar. It again smooths out the transition between log k and S Bekenstein-Hawking. So the second question was, how far can you take this semi-classical approximation? And I guess it depends what you're trying to compute. So in JT gravity, you can actually do the full quantum calculation. In this model that we discussed, you can do the full quantum calculation, and the results are similar to what we showed. For more interesting theories of gravity, it's harder to go beyond the semi-classical approximation, but I don't think there's any problem with these replica wormholes. In the semi-classical approximation, they look just fine. There might be a problem if in a part of the moduli space where the wormhole is long and thin, but that's very far away from the classical solution, so it probably doesn't affect the conclusions too much.
My basic question is that this bottom-up approach is not strong enough to perhaps reproduce all the results that you expect to have in the full quantum theory. Is that right?
Yeah, that's right. So we don't get the discreteness and the microstates this way. It's really a strange situation where the semi-classical gravity seems to be computing for you some kind of average theory of the microstates, but it doesn't have the capacity to describe the exact theory with the individual microstates. And I don't really know what to say about that. Basically, I'm not the right person to talk to about that. There are people who think hard about this and have much better ideas, and it's not me.
Thank you.
Okay, so since we are running a bit late, and since Douglas is going to give the tutorial anyway a little bit later, my proposal will be to postpone the remaining questions to the tutorial and take a short 5-minute break before we resume. So please, well, remember your question and ask it a little bit later today. Now we will split into 2 different rooms. You already know, if you have been assigned to